We're also doing a lot of work to extend the spatial and temporal coverage of these plot-level indicators using sensing approaches. The rangeland analysis platform is one example of these tools. It's an artificial neural network model trained on the monitoring data to produce annual predictions of plant functional group cover across the Landsat archive and the Sentinel archive, which is more recent, and it includes a 16-day production model. So this enables us, or users, to gain a better understanding of the spatial and context of trends in communities across the landscape as they're varying in the context of the treatments and management practices that people are applying. A second major challenge that managers often have, and general users have, in interpreting these indicator data sets is not necessarily knowing what indicator values should be for their landscape that might indicate degradation processes or responses to drought and so forth. So we've been doing a lot of work with various agencies and stakeholders to identify approaches to setting benchmarks that enable them to identify in objective ways what the condition of landscapes are, what their trends are, and to make actionable decisions based on those data. And in this context, we're defining benchmarks as indicator values or ranges of values that describe the desired conditions that, if they're exceeded, might trigger a management action. They could trigger additional monitoring, data collection, or they might indicate management success. And we've found that we get greatest utility in establishing these benchmarks if we tie them to the land potential and the ecological dynamics of sites. So in this context, we define land potential as the potential productivity, the degradation resistance, and the potential resilience of sites, as described by their soil properties, their climate, their landscape position, and so forth. And we describe ecological states as representing the effects of different processes on ecosystems. And these effects can be represented in state and transition models like that on the right-hand side of the slide here, which connect particular degradation drivers and restoration options and management practices to the ecological state of the system. So we can use our monitoring data sets to identify benchmarks based on indicator values like those shown in the state and transition model that represent perhaps desirable ecological state characteristics or just the characteristics of the states. We can also set benchmarks based on process thresholds or other ecological thresholds between states at which processes impact certain ecosystem functions. So this could be wind erosion thresholds and their association with ecological state changes. So in practice, by linking land potential and ecological state concepts with our monitoring data, managers can visualize the distribution of different indicators for different ecological states of a system, and from there, perhaps identify those that they consider to be suitable given their management objectives, those that might be at risk of certain degradation processes like wind or water erosion or exotic plant invasion, and those that are perhaps simply unsuitable given their management objectives. So we're making these data and these kinds of interpretive tools available through the Landscape Data Commons, which is an effort that's been in development for about 5 years now that seeks to harmonize and aggregate the different monitoring data sets and connect them with different interpretive tools for managers. So we have a public data portal with our goal being to make as many of these data sets as publicly available as possible. We also have an API that more advanced users can access, including the raw data behind the indicator data sets. One of the interpretive tools that we've built that sits on the Landscape Data Commons is a benchmark exploration tool that enables users to query the database for a certain area or a certain period of time, visualize graphs of different indicators of interest, establish benchmarks for those indicators, and then apply them to their management area. A couple of other tools that we're linking to are the US Geological Survey's Land Treatment Exploration Tool. It's a tool that's designed to help managers plan restoration and rehabilitation treatments on the landscape, as well as the ecosystem dynamics interpretive tool, which is a database that houses ecological site descriptions, which are a classification of land potential, and state and transition models, which have been developed for those specific land units. So the idea here is to tie the monitoring data to soil properties and climate and the land potential, and then from there enable interpretation of those data sets in the context of the ecological dynamics and the drivers of those dynamics. Our broader goal here is working on the premise that improved data access can enable more data insights in an adaptive management context. And the goal, of course, in this setting is to enable managers to prioritize actions on the landscape. So by combining the monitoring data with land potential information, they can identify which parts of the landscape are resilient to certain degradation drivers or drought or other processes. They can identify management options that may support that resilience in the landscape. At the same time, they can identify parts of the landscape that are at risk of certain degradation processes or might be particularly susceptible to drought that might induce an ecological state change that might be less desirable, and iteratively the landscapes, learn from the data, combining that with their local knowledge and understanding of ecosystems, and adapt management to meet their management goals. So in practice, we're working both at the plot scale and spatially to enable users to identify land potential across the landscapes, identify and understand the relationships between different ecological states on the landscape and the drivers of the state transitions, so that's the state dynamics, and from there identify which practices might be most suitable for maintaining their desirable ecological states, which practices might be suitable for inducing a state change, if that's possible, and which practices might not be suitable because they're less likely to be effective given the dynamics of a site. So incorporating data into this process, managers can track trends in certain indicators of the landscape, identify when state changes occur, learn something about the drivers of those state changes, identify where there are risks, for example, from soil erosion on the landscape, and from there set and adjust their management goals at scales that are appropriate to the land potential and the ecological dynamics of those sites. So to wrap things up, sort of back to our question that's driving this research of how can we use big ecological data sets to support adaptive management. Working with various stakeholders at different levels, we've identified through this work that really integrating big data tools or integrated big data tools in the hands of managers and scientists can provide more ecological information, enabling incorporation of monitoring data and additional sources of information alongside their local understanding of ecosystems. This can increase the utility of data sets for management, enabling more participation of different stakeholders in management decision making, supporting more agile or adaptive management decisions across the landscape. So I'll finish there and thank you very much for your time.
Thank you very much, Dr. Nicholas Webb, for your informative presentation. Now, it's my pleasure to introduce Dr. Mu'tasim Ashfaq, a senior research scientist at Oak Ridge National Laboratory. Please join me in welcoming Dr. Mu'tasim Ashfaq.
Thank you very much. So my presentation is a little bit more technical, but covers a very important aspect of the Earth system that has not been explored much.
The green one is forward, the red one.
Okay. So drought, as we all know, is one of those climate extremes that can potentially have a very lasting impact on both natural and human systems, depending on its severity and intensity. But when drought happens over multiple regions simultaneously or sequentially, we call it a compound drought event. And a compound drought event can have much more severe implications for these natural and human systems than a single drought event over a region. Because it puts immense pressure on global food systems, reinsurance industries, and regional economies. One of the recent examples of the compound drought is from 2015, as I show you on the top right panel, when multiple regions across the globe were experiencing simultaneous droughts. This included Western United States, Brazil, South, East, and West Africa, Australia, Europe, and parts of Asia. And because of multiple regions experiencing drought, it led to shortages of key agricultural commodities across the globe and increased their prices. For instance, Brazil, as you may know, is the #1 producer of coffee beans. In 2015, because of the drought, it had a reduced production of coffee beans that led to increase in coffee beans prices across the globe. Similarly, maize is a major crop in the United States and in parts of Africa. And in 2015, there were major losses to this crop, and that led to increase in the maize prices in global markets. Similarly, thousands of animals and livestock perished in East Africa because of very severe and extended period of droughts, and that led to increase in meat prices in regional economies. So through these examples, what I want to highlight that a compound drought can have a ripple impact on global economies. So if we want to develop resilient communities and if we want to cope with the challenges that this kind of event may have on global food systems, we really need to understand the characteristics of compound drought, what are its drivers in the historical period, how future increases in greenhouse gases may impact its characteristics, and what does that mean for the agricultural and human systems. So that's the topic of my presentation, and it's based on 2 collaborative studies that we did in recent years. So in the historical period, we focused on last 40 years or so of observed climate. We used multiple precipitation and temperature data sets, but as you may know that a compound drought event is much more rare than a single drought event. So only focusing on like 3-4 decades is not going to enable us establish a robust understanding of this phenomenon. So what we do that in addition to these multi-decadal observational analysis, we also use a 1,800-year-long model simulations to understand that whatever we see in the observations, whether there's a robust identification of those drivers in the model simulations. So we are not focusing on all the regions. We only focus on the regions where a major fraction of precipitation comes in summer months. We only focus on summer months. And for identifying droughts, we use a commonly used index called Standardized Precipitation Index. And if 3 or more regions simultaneously experience drought, based on this index, we call it a compound drought event. And then using different thresholds, we identify whether the drought is widespread or whether it's severe. So on the bottom panel, you see the regions that we have used in our analysis. In addition, you may also see some blue rectangles over tropical oceans. These are the natural drivers of climate variability in the Earth system, and we focus on these drivers to understand how they may have a role in causing these compound droughts. So what you see in the top panel is the occurrence of drought in the historical period over the last 40 years or so. And all these gray stripes represent the time periods when we experienced compound droughts. And you may notice that at least there were 3 times in 40 years or so when the globe experienced major compound drought episodes, including 1982, 1996, 97, and 2015. And in the bottom panel, you see all those regions where these drought was occurring simultaneously. And you can see that at least in these 3 cases, 5 or more regions were simultaneously experiencing widespread droughts. Now, we wanted to understand that how different atmospheric and oceanic modes of variability have impacted, might have impacted the occurrence of these droughts that we are showing here. The top 3 rows on this panel represent different characteristics of droughts. If there's a white dot, that means drought was either severe, it was widespread, and it was a compound event. And the bottom rows represent whether there was a presence of a natural mode of variability. So, for instance, if you look at the bottom row, which is ENSO, one of the most potent Earth system mode of variability, you can see there were 11 episodes of compound droughts in these 40 years, and out of these 11, 7 times there was ENSO present. There were other natural modes of variability also present, but those were less frequent. So that means ENSO is perhaps the most important driver of compound droughts across the globe. Now, as I mentioned earlier, this is only 40 years of data, so although this tells us qualitatively that ENSO may be a major player, but unless we look at this in a long simulation, we would not be able to identify its robust connections. So that's what we do here. This is based on now 1,800 years long simulation, and 3 panels represent the frequency, the spread, and the intensity of the drought. So one thing you may notice, the gray bar, it represents what happens when there's none of these atmospheric or oceanic modes of variability present. And you can see the probability of experiencing a compound drought is very minimal. So that means that these modes of variability play a major role. Second thing you may notice that among all the drivers, their individual contribution, ENSO is the most important driver. ENSO is the one that causes single-handedly most frequent compound droughts, and those are not only frequent, they can be severe and widespread. But you may also notice in the last 3 bars that when ENSO is present with other modes of variability, then its impact is compounded. So the droughts become more frequent, and they become more widespread and more severe. And if you look at the last column, you may notice that when ENSO's positive forcing, which is known as El Nino, when it co-occurs with tropical North Atlantic forcing, its negative phase, then there is a high probability of these compound droughts, which are also very severe and widespread. So, in summary, what I've tried to explain that, one, there have been multiple compound droughts episodes, so those are real climate extremes, and ENSO appears to be the main drivers of these climate extremes. But when ENSO occurs with other modes of variability simultaneously, then these droughts can be more severe and widespread. Now, for the future period analysis, we again use a very long model simulations, which we call large single model ensemble. This represents almost 1,200 years of 3 time periods that we analyze to understand how compound droughts may change in the future. We also use agricultural data and future climate projections to understand that how changes in the characteristics of compound droughts may change the exposure to these extremes to the agricultural land and human population. But one thing that we change in our methodology is now that instead of using only precipitation-based index, we use a drought index that also considers temperature, because we know that in future, drought may not only be because of precipitation deficit, it may also be because of increase in evaporative demand. So, okay, I don't know why it's not that clear, but what is shown here is, again, the frequency, the spread, and the intensity of the compound droughts. In the right, the red column represents that what may happen in the future. It's not very clear, but you may make an idea that yes, in the future, if there is no change in the path, the way we are increasing greenhouse gases, then there will be substantial increase in the frequency of compound droughts. The last panel represents the severity, and you can see that the number, which may not be clear, it means actually that every 3 out of the 4 droughts in the future would be very severe drought. But interestingly, what we see that there's not much change in the spread in the compound droughts. Okay, unfortunately, again, this also looks not very clear for some reason. But what I'm showing here is that, is it clear? Okay. So what I'm showing here is that how these changes in the compound droughts would change the exposure to agricultural system and human population. So what it shows that by the end of 21st century, the exposure that agricultural land has today, it will have 10 times more exposure by the end of 21st century. And also, human population will be 9 times more exposed to these compound droughts by the end of 21st century. But remember that in the future, the change in exposure to human population may only not be because of changes in droughts. It can also be because population is projected to change. Over some regions, it will increase substantially. That should increase exposure to these droughts. But there is a substantial variation across the regions. We see that over Americas, Northern and South America, these exposure to compound droughts would be much more severe. But then other regions like Northern Africa and Asia, the exposure to compound droughts would be less severe. And part of the reason is that we, as you may know, that over Asia and Northern Africa, precipitation is projected to increase substantially. That would compensate for the increase in evaporative demand by the end of the 21st century. Now, we want to understand how ENSO would have an influence on the characteristics of compound droughts. So what I'm showing you here is the distribution of ENSO events in the present time and in the future on the left side. And you can see in the future period, and the PDF has flattened and it has become more fatter. That means that not only we will have more ENSO events, those will be more severe in both La Nina and ENSO events. And that's going to lead to more severe compound droughts. What we expect that every 3 out of 4 El Nino events will be associated with a compound drought by the end of the 21st century. And the part of reason why ENSO is still able to exert substantial influence on compound droughts is because its teleconnection is going to stay stationary. What I'm showing on the top panel is the ENSO's teleconnection in the present time. In the bottom panel is the teleconnection in the future time. And you see it remains stationary. And on the right side, we see that how it varies across the regions. And if the dots are falling on the diagonal, that means there is no change in the ENSO teleconnection. So to summarize, what I've showed you in the second half of the presentation, that what we see that in the future there will be more compound droughts if we keep on increasing greenhouse gases as they are happening right now. And that will be mainly driven by increase in ENSO frequency, ENSO intensity, and increase in temperature. That's going to increase the evaporative demand.
Thank you, Dr. Ashfaq, for your excellent presentation. Next, I'm pleased to introduce Professor Fred Kucharski, a senior research scientist in the Earth System Physics section at the Abdus Salam International Center for Theoretical Physics in Trieste, Italy. Please join me in welcoming Professor Fred Kucharski.
I would also like to thank the organizers for giving me this opportunity. And so I'm presenting this work here, which has also a climate and a technology component. But my background is really, I'm a climatologist, so I'm mainly focusing on the climate impacts of this study here that I'm presenting, which is the impact of wind and solar farms in the Sahara Desert on rain and vegetation. Now to provide this is the feedback, many co-authors. And so the study region would be the Sahara Desert, but potentially also relevant for global desert regions, for other desert regions, to be verified, actually. I will start to look at something that has happened in the Sahel region, because this is also relevant to this study. So the Sahel region is this red-colored region that is the transition between the region where it's raining a lot and the region where it's raining less, so a very comfortable region where farming is very well possible. So if you look at the average rainfall in this box that I've just shown over the last century, this is for the summer rainfall in that region, you will see that there's a very interesting behavior and very also important behavior of this time series of rainfall. So there have been periods where this region has been extremely wet, let's say in the 1940s, 50s, and 60s, in regions where, periods where this has been extremely dry. And the interesting part is here that these droughts have been for decades, so different from Motasim's previously presented work. Here we are analyzing droughts that are lasting for decades, actually, not just for a few months or years. So it's a very relevant behavior. Now it's thought that also these droughts and wet periods are related to mainly related to internal climate variability phenomenon. Only that it's not ENSO, but it's the decadal component of ENSO. So we call it maybe Pacific decadal oscillation or interdecadal Pacific oscillation and the Atlantic multidecadal oscillation that can be relevant for these long-lasting droughts. But model experiments have shown that you cannot model the strength of these droughts unless you allow for land surface and vegetation feedback. They can amplify these droughts by a factor of, let's say, almost 5 or 10. So without those feedbacks, you will never be able to get the strength of this drought. There may be also a climate change component. This is still under investigation, but it's thought that the main component is related to these internal variability modes on decadal timescales in this case. If you look how this spatially look like, on the right side here is the mean rainfall in the region, and on the left side is the change that has happened if we look at the 1990s, 80s, and 90s with respect to the 1950s and 60s. And you see this red color means really a substantial, widespread drying. So it's not some kind of phenomenon that is dominated by local adjustments, but is a very widespread drying. And some redistribution between the equatorial region and the region to the north also. So why is the Sahara? The Sahara is a very sensitive region with respect to climate variability, because there are these drawings in the middle of the Sahara in some of the caves, which shows that maybe 6,000 to 10,000 years back, the Sahara was actually vegetated and there was farming going on. So it's a very sensitive region, and the reason why this has happened is supposed to be small changes in the orbital parameters. So now I'm coming to the heart of the study that I would like to present. So as we know that if we concentrate on the, is there a pointer? Maybe not. On the right curve here, the CO2 curve is just going up and we don't really know what to do in order to make it reduce. And this goes along with the population growth. This is nothing at all new to you. And as we also know that energy accounts for most part of this energy increase demand, accounts for most of this CO2 and greenhouse gas emission increases, and most of the energy is actually coming from fossil fuel burning. So we need renewable energy in order to be able to solve this problem in some ways, apart from carbon sequestration, which was mentioned also before. So the idea was, so what's happening if we cover a desert region, like a huge desert region like the Sahara, with wind farms and with solar panels? How will it impact the climate on Earth? And so essentially there are two effects on climate that are relevant here then. The wind farms would impact the surface roughness, and the solar panels will impact the surface albedo, and both would have impact on the climate. And so the reason why I'm part of this is actually that I've developed the atmospheric component of a model that we will be using to investigate the feedbacks. So these two feedbacks, they have a very long history. Already Charney proposed that maybe there is this feedback, the well-known Charney feedback. So if we, for example, destroy vegetation, that will reduce the surface temperature, that will cause abnormalist sinking motion in that region, in this case in the Sahel region probably he was thinking about. That will reduce vegetation, that will reduce rainfall, and that will reduce vegetation further. So there's a positive feedback, the positive Charney feedback that is relevant here. The same thing is true for the surface friction. So if we reduce vegetation, we reduce the surface friction. That means we reduce the surface convergence in that region. That means, again, anomalous sinking motion and less rainfall and less vegetation. So these two feedbacks may be relevant. In fact, as I just mentioned, the solar panels and the wind farms, where they will interact with these two feedbacks. And we think that they may act both to have then an impact on what we find in the model. So that is the implementation that we then do. Finally, so in our model world, it's a very coarse resolution model. The Sahara Desert has been identified on the right panel there. So we have a very coarse resolution model. So these experiments should be repeated with higher resolution models and with more sophisticated models. And so we use that region to cover them largely by these wind farms and solar panels. However, the solar panel coverage is only 20% of the region. So the vegetation would have a chance to grow between the solar panels that are actually implemented. So what is the response? And it is found, interestingly, that if we look at the rainfall here in the lower panel, the rainfall response shows an increase, apart from a warming because of the lowering of the albedo. There is a large-scale increase of rainfall in the region where we put the wind farms and solar panels. So there's a very strong positive feedback, reminding a little bit on the wet Sahara period. So a small change in the climatological features in that region may be enough to go back to a situation where the desert is actually green in this case. And the physical mechanism is actually that both the solar and wind farms, they increase the vegetation in that region, and that causes even this further strong feedback by the vegetation through the Charney and the Sud feedback. Yes, so it's shown the albedo is decreasing, the vegetation cover is increasing, and this holds for both individually the wind farms and the solar farms. They both contribute about equally, a little bit more the solar farms in this case. So this is again a summary figure of this result. which was very surprising. And so I just want to conclude with some critical comments that we received. So we have shown that it is possible to have this very ambitious project to cover the whole Sahara Desert, almost impossible project actually, with wind farms and solar cells, then that would have locally a positive impact and reduce desertification in that region. However, had been criticized that the numerical experiments that we performed are with a relatively coarse resolution, simple model, and not coupled to the ocean, actually. So I'm not aware that it has been repeated as of now with a, let's say, more higher resolution model, more sophisticated model that also includes ocean dynamics and so on. The problem with that is that it's extremely costly to run a model that is coupled to interactive vegetation, and it allows for possible drifts in the model and so on. So therefore, many centers are actually reluctant to make this effort. Yes, and there will be many criticisms has also objected that probably it's not, the implementation of this project is not feasible at all because it's just too big. And for example, what about the maintenance of the solar panels? So someone should go there to maybe clean the solar panels from time to time. So maintenance may be extremely difficult. So the whole thing is to be further investigated. Thank you.
Thank you very much, Professor Kucharski, for your enlightening presentation. Now, it's my pleasure to introduce our next speaker, Dr. Saeed Munir, who is serving as an air quality and meteorology expert at the National Center for Meteorology. Please join me in welcoming Dr. Saeed Munir.
Thank you and good afternoon, everyone. First of all, thank you to UNCCD, NCM for arranging this event, for bringing us all together. And thank you all participants for coming together. You saw a different presentation about different part of the world. I'll be focusing on Saudi Arabia. How is, the weather parameter, meteorological parameter, how they are monitored here and how they are been changing through the time and how they are changed through the, in both space and time. As you can see, the title, Drought Dynamics in Saudi Arabia, Current and Future Trends. Because at the end, I will be also talking about what the model says about the future of drought in Saudi Arabia. Okay, so this is a bit of the introduction. Spatial and temporal trend of precipitation in Saudi Arabia. Various drought indices. This is very important because it's not only precipitation data I'll be using. I'm using various drought indices to see how they actually compare and what they actually indicate through the 40 years of time, and how actually different indices, they actually correlate with each other. And then I will talk about the long-term temporal trends, future projection, and then at the end, some recommendation how can actually be address the issue of drought in Saudi Arabia. Okay, so you can see the map. National Center for Meteorology, we have an extensive network of monitoring stations. There are 26 monitoring stations which provides over 40 years of data. Hourly data, daily data, monthly, and you can see the color of the map actually show the elevation, how Saudi Arabia elevation changed from east to west, and you can see gradually toward the west, there's a high elevation, and you will see later on there will be more precipitation. Okay, so this is the precipitation data. And as you saw in the previous slides, there was the east to west trend in the elevation, and you can see that the precipitation data also in the western, especially the southern western side, Jeddah, Makkah, and this Taif, this area. About this is the area which receive more rainfall. Okay. Right. To quantify the drought, we calculated 26 indices. Okay. Obviously, probably some of you will be aware SPI and SPEI. So we did a lot of analysis using our R programming language. Thanks to two of my colleagues, very young, very dynamic, and very, mashallah, enthusiastic, Asil and Nuju, they helped me a lot in these calculation. So we calculated, the 20 of these indices, and then correlate them. Okay, and interestingly, they present a very good structure, very good clusters, and clearly there are 4 main clusters. Okay, so the first cluster, which you can see the AI, irradiation index, EDI, PNP, and SAI. And then the next cluster, the chain hazard index, decile index, and RDI. And after that is the Palmer index, PDSI, Palmer Drought Severity Index. So that's another cluster. And in the end, SPI and SPEI, they make another cluster. Okay. Obviously, it depends, on the algorithm of the calculation, how they actually calculate. Right. This is the precipitation data, and how actually you saw earlier the spatial trend, but this actually shows how actually the precipitation changed over the year. Okay, so apart from Aba, which is a very high altitude, all the other monitoring stations, they show very low precipitation during the summer and higher during the spring and winter. And this is basically the typical cycle we observe here in Saudi Arabia. So using one index from all those 4 clusters, so SPI, which is the top left, and then PDSI, the next one, EDI, and CZI. So we just pick one index from each cluster, because there's no point repeating all of them because they have very strong correlation with each other, right? And we can see that this is the data that I just presented for the last 40 years, from 1985 until 2023. And the Abha, which has the highest altitude, and you can see that the trend is actually negative, right? So the SPI trend, minus 0.02, and highly significant. The PDSI Palmer Drought Severity Index, minus 0.05, again, negative and highly significant. And similarly, EDI, negative, slightly weak, but significant. And then China Z index is the only one which didn't show any significant trend. Similarly, I repeat the same for Medina, which has like the median sort of altitude, and the results almost the same. So SPI, negative, PDSI, negative, and then EDI and China Z index, they showed no significant trends. Dammam, one of the lowest altitude, but it also shows almost the same trend. Okay. Finally, I also show Riyadh, because we are here in Riyadh, so I thought some people would like to see what actually Riyadh's data shows. And it's almost the same trend, SPI and PDSI. And actually, this interesting point, when we are considering the different drought indices for calculating the spatial trend and the temporal trend, this is very important if we understand our indices, how actually they are calculated, what are the parameters they use, is it only temperature, is it only precipitation, or there, there potentially evapotranspiration. So, because we can clearly see that the chain hazard index is not that sensitive to the change. Secondly, EDI is after the chain hazard index, and then PDSI and SPI. They are actually the two indices which are sensitive and which can actually show that actually the trend is significant. Okay, and then over all the 26 monitoring stations that we had data for, and you can see here because the graph, probably you don't see the detail, but here I just summarized. The positive significant trend was only Gizan and Najran, okay? So although majority of the station, which is then the next one, which is negative significant, and there are also some non-significant, but only two stations, Najran and Gizan, they showed positive significant trend. What it suggests actually, that when we define, or introduce new policies, we need to take local variability, local spatial variability of these local area like Najran, Jizan, Riyadh, where actually these areas are, rather than making one overall policy for all the area. So this is a very important point which I could see from here. Similarly, PDSI, there's no positive significant, but most of them, or all of them actually, they were negative or non-significant. Again, EDI only in Najran and Yambu. Chain hazard index, it shows like, the chain hazard index was one of those index which is now very sensitive to the changes in the variability and of the variability and the precipitation trend. Apart from this, all other indices that actually shows significant trend. So now, if you look at the spatial variability of these four indices, you can see the SPI. It shows, quite a few of the area they're actually positive. This data is only for 2023, the last year. So I wanted to see actually how is, the drought changing in the last year, 2023. So the SPI, it shows, okay, 2023 is one of the year where drought has decreased. And similarly, the same result have been shown by EDI. But again, it's the chain hazard index and the Palmer drought severity index. It shows, again, drought in many areas of Saudi Arabia, even for 2023. So there is a technical side of it, which index I should be using, and there is a policy side of it. Okay, let's talk about now, so that was the trend. The data was talking, it was showing actually how drought has been changing during the last 40 years. Now let's see what the model says about the future projection. Here we use CMIP4 model, CMCC, MCM, MPI, and OESM2. Okay, and we use the model mean of these using three shared socio-economics pathway, SSP126, SSP245, and SSP585. And the duration for this projection, future projection, is 2026 to 2099, 2025 to 2048, so like a near future. Oh, sorry, 2026 to 2029, the whole period of projection. So the 2025 to 2048 is the near future projection. Then from 2051 to 2074, the mid period or the mid future, and then finally the end of the century, 2076 to 2099. Okay. So there's a bit of hope at the end of the century, but the model projection, thanks to Dr. Kamil for producing these projection, actually it shows like the negative trend gonna carry on for some time. Okay, so the near future shows further increase in drought. After that, there will be a period that actually the trend will decrease, it will turn around, and then at the end of the century, there will be lots of rainfall and the drought will go away, according to these projections. Okay. Now let's talk about a few recommendations. How can actually we address this issue? So the first one, effective management of climate change and its impact. For the last couple of days, we've been talking about climate change. How can actually we manage climate change? How can we manage its impact? So that's very important because that's directly related to the drought. Reducing reliance on groundwater by developing alternative water sources. Planting more trees and restore degraded land. Shift from water-intensive agriculture practices to more sustainable methods by introducing more efficient irrigation technologies. I think all these points are very simple, and so I'm not going to try to explain them. They are self-explanatory. Investment in desalinization and wastewater recycling. Enhancing water use efficiency in agriculture, industry, and urban sector. Obviously, you know, majority of these, they will need policy intervention from the government side, not only from the Saudi Arabia government, who has already introduced several interventions, like the 2023 vision, 2030 vision, and the Green Initiative of Saudi Arabia and the Green Initiative of Middle East. But it needs like a regional and international cooperation to implement these recommendations. Number 8, establishing a regulatory framework for monitoring groundwater use and restricting over extraction. Capture flood water by constructing large dams and reservoirs in the country. Comprehensive drought monitoring, modeling, and early warning system, part of the scientific community work. Developing sustainable urban planning that integrates green infrastructure such as urban parks, green roofs, and permeable pavement to reduce runoff and efficiently collect and manage stormwater. Okay, there are a few more. But the time is limited, so I'm not going to go through all of them. Thank you very much for your attention. Thank you very much.
Thank you, Dr. Saeed Munir, for your excellent presentation. Once again, I'm delighted to introduce our next speaker, Professor Turki Habibullah, the General Manager for Research, Development and Innovation Directorate at the National Center for Meteorology. Please join me in welcoming Professor Turki Habibullah.
Thank you, Amal. Hello again. Yeah, this one. Okay, brilliant. Yeah. So, yeah, my presentation is going to be just divided into two parts today, regarding to just precipitations in 28 stations, and then we will go inside strategies how can to prevent desertifications, combating desertifications. I would like to thank Dr. Kamil, Dr. Saeed Munir, just for helping me just for some analysis. Everybody knows droughts, just let's say precipitations and shortage of water sources. Yeah, those two parts can get droughts easily. What are the main factors contributing droughts? I think climate change, yeah, deforestations, and let's say civilizations, yeah. Increasing of buildings, yes, can increase the desertifications. High temperature atmospheric phenomena. Let's go just directly to, we have used 28 stations. Dr. Saeed mentioned that one. The main stations, which is moderated by NCM, National Center for Meteorology. And if you can just see the distribution of all these stations, yeah, in Saudi Arabia. Let's take 2 or 3 stations, and we're going to see what's the positive trend or negative trend. We have used just 2 scenarios. One scenario is from 1985 until 2023, and the other scenario from 2010 to 2023. And in RR, this northern area of Saudi Arabia has positive trend precipitations for the scenario number 1, which is positive, and trend precipitations for that one also positive. Negative trends and precipitations in Riyadh, which is here, in the city. So both in 2 scenarios. And if you can see here, temperature trends, precipitation at different sites, KSA, we can see we can see all these stations, and P stars, going to be negative and positive. And for this one, if you can see, so no significant in Abha, and significant at Al-Baha, for example, or Al-Hassa, for example, and significant at B value in Jizan. And you can see this August, we had a very huge precipitations, reached to 414 millimeters just in 1 month in August, just in Jizan, which is the southwest area of Saudi Arabia. And this is just a trends for just regarding to differences in value. If you can see, just the high differences, which is in the MAM. I need just to go through, to go quickly to strategies. If you can see here, trend of precipitations. 6 months, May, I think, is going to be just less precipitations. 6 month indicator negative trends, and 6 month positive trends. And the positive trends, during December, of course. This picture is familiar. This figure is familiar. So precipitations, 1985, 2010, 2023. If you can see in 2023, a huge amount can be affected in southern southwest, also in the middle, which is abnormal. We call it abnormal weather during this month. Also here, these are 2 scenarios. For the second scenario, you can see it's abnormal weather and the huge precipitations in the middle. We can go to the second part of this presentations, which is, okay, we need approaches for addressing droughts, and these strategies can be, let's say, locally or nationally or regionally. For local levels, community and city scales, of course, we can use 5 strategies for that one. The first one, we can use smart irrigation system. For example, installing IoT-based promote trips and subsurface irrigations. The second one, rainwater harvesting, urban green infrastructures, community water management. For example, education. Educate local communities. We have to educate people, okay, how can you survive and get low desertifications, establishing cooperatives for farmer to collective management. The final things are going to be desalinations for local use. Of course, we need to provide clean water for drinking and farming. We move now to the national level, which is government and policy scale. Also, we have here 7 strategies. So we can, regarding to a national water reuse program, expand wastewater treatments. Yes, this is a goal of government. How can we expand treated stations and get green water rather than gray water, and then large scale desalination, cloud seedings. As you know, NCM running cloud seeding program, national cloud seeding program, and we are targeted many areas in Saudi Arabia. They have started 2 years or 3 years ago, and they have continued just to target new areas in Saudi Arabia. Drought early warning system. We have announced about early warning systems yesterday, which is this year is 14 years we are running this system and give a warning issues to all local and government area. Regarding to water, pricing and subside reforms, implementing tide water pricing, subside water efficiency. The second, 6 aquifer research projects, which is create artificial recharge system to replenish groundwater. The final one is going to be a national afforestation compassion, which is a large-scale tree planting program. For the large regional level, which is cross-bordings, there are 6 strategies, which is GCC water grid, develop shared water grid among Gulf Cooperation Council, GCC, regional drought resilience fund, we got fund, shared data. Of course, everybody talking about sharing data. How can we share data in GCC, and what strategy can get data? Joint water desalination program projects. The final one, which is, let's say, regional transportation belt, develop a green belt. How can the scientific community help address the drought issues? Enhancing drought monitoring, yes, of course, we need to increase the monitoring, develop and improve climate models. Of course, we are using models for climate, for weather at NCM, just to predict droughts patterns, and instead using AI, machine learning, remote sensing, early warning system, which I have mentioned just earlier, and data sharing platforms. I think MIWA, Ministry of Environment, Water, Agriculture, announced about data center, and we can use sharing data by this data center, create, which is a platform for sharing weather. How can the scientific community help address the drought issues? Also, water resource, groundwater recharge, solutions, innovations. We're focusing about innovations too much regarding how can to increase the innovation and help protect lands and combat desertification. How can the scientific community help also? How can the scientific community help address the droughts, which is ecosystem, here ecosystem is here, affording soil management, wetland creations. How can the scientific community also the policy support and public awareness? And the 6th one is going to be renewable energy integrations, which is climate agreements, energy, water, nexus, solar board solutions. And a summary, as I mentioned, 2 scenarios. Both of them has some stations, few stations get positive precipitation, and the other one get negative precipitations. And here, this is a final slides, which will increase of precipitation, more promoting central area. Further investigation should be implemented at local, national. Many thanks indeed for your listening. Thank you.
Thank you, Professor Habibullah, for your enlightening presentation. Next, it's my pleasure to introduce Professor Sudeep Chakrabarty, who is currently serving as an associate professor at the University of Calabria, Italy. Please join me in welcoming Professor Sudeep Chakrabarty.
Thank you very much. for the introduction. Okay. So, first of all, thanks to COP and National Center for Meteorology for the invitation. And thanks, Professor Munir and Turk, for make my life more easy, because you already introduced some of my technology that I'm going to discuss here. So that is like some of your recommendations and some of also his national policies. So I'm going to discuss about how we can, I mean, we're talking about the deforestations, no? Like how to make it less deforestation in this case. But I want to talk about how to recover the water, to use it in irrigations as well as for the daily use. So, and also as Munir Turk said, that we need to go to the community. So I think that's what I mentioned in the topics and the presentations, that science to society, because we have to reach to the society in our case. So I don't want to talk more about these techniques that, I mean, they already discussed, so I will not go more details about the hotspot, because we already discussed these things about also like 9 out of 10 water climate change related issues is related to water. So I will not go over even more details in this case. I will go directly in my presentation. So I will talk about like more about how to purify the water. So I suppose that here many people knows about membranes. They talk about desalination, but we need to keep our attention in this technology, how we can reuse the water. So we are trying to capture the water from everywhere. We are trying to use different nets from the fog water. We are trying to get the water from the sea. We are trying to get the water from the different like solar panels. We are using new technologies, but we have to improve the attention like to the innovation or new way of life. So digital water solution in this case. So we know membranes. So membrane is a kind of semi-permeable or permeable barrier that can protect something to allow on the other side, whereas they can remove some particle that is not necessary. So that is one of the reasons that I think seawater desalination is coming. Not only that, there are other techniques like nanofiltration, microfiltration. So we are working on different techniques from different funding agencies. We have a project now related to textile industrial wastewater, so pharmaceutical industrial wastewater, to reach the TRN level from 8 to 9. So that means we are going to reach the commercial level with our membranes. So how we can do this? So okay, this is the as I mentioned before, that this is the membrane. So membrane is like if you see that the green part is the membranes. So on the feed side, there are a lot of other big particle and small particle, which is going through the pores of the membranes, and we can reduce the bigger particle to retain in the others in the feed side, whereas we can get the permeate side, which is more clean. So this is not usually happen. We need to use it for irrigation. So we can even use the clean water. That doesn't mean that we have to use the drinking water for the irrigations. So, but there are some problems for this. We have fouling. We have the like operating temperature, pressure. They have the short lifespan. So we are trying to improve the membranes by our new technologies that we are innovating. So we are having different patents on these technologies, that we are using new materials. We are developing new technologies, catalysts, to incorporate it in the membrane surface, membrane pores, so to make it more energy harvested, more green, so that it separate different particles. So as I mentioned before, that we have different kind of membranes. So one is UF, MF, NF, and RO. So whatever you are saying about the desalination, that is coming to the RO membranes, which is very high cost membranes, because you need to use a lot of pressure. But to use in irrigations, to use in deforestation technologies, we do not need that much water that comes from the RO membranes, but we need some water that can reduce the bacteria, virus, macromolecules, nanovalent, divalent ions. So that can be used also in irrigations. So in our case, okay, this is already discussed. So in case of MF, we usually use the techniques that is ozonations, UV. In case of UF, we usually use sun filters. But in case of reverse osmosis, we use the different ceramic membranes that comes from a very, how to say, the cost. The cost is very high. So these are some techniques that for the drinking water processing, we need to use the from the different surface water or the groundwater. But from the wastewater, we can use the wastewater from different industry. It can be pharmaceutical industry, it can be textile industry, it can be different food juice, food industries as well. So these are the different desalination technologies or the figures from different plants that we have taken during our different visit of the plant things. And this is a membrane system that we usually use to integrate it at our home, so in our house. So from the municipal wastewater, we can get also fresh water. It cannot be, there does not need to be always the fresh water to be drinkable, but it can be used also in irrigations. I think some of the, like in UAE, they are using some of this technology to get the water and to get it in the, to give it in the gardens. So in our case, we develop our membrane by ourselves. So this is the structure of different membranes that we develop by ourselves in our laboratory. So those are like porous materials. Sometimes also we develop some of our polymers by ourselves. So we incorporated different nanoparticles to make it more cost effective, make it more efficient in terms of reactions mechanisms. Also, we are developing different catalysts. So that catalyst, we can incorporate it in the membrane pores. So as you can see here, that they have different channels. So within that channels, if we can incorporate a different catalyst, suppose it can be biocatalyst, it can be inorganic catalyst, it can be any kind of catalyst, that can separate or do the reactions that you need. So based on that, we can even design the membranes. We can even engineer the membranes starting from UF, MF, until the NF, even our membranes. So we have that project that I mentioned before. I will give you some example now here. In next slide, I think this one, that we have a project from the Prima Foundation. It is more 2.5 million of euros fund. That is to reuse the water in Mediterranean context. I think Tunisia is one of the partners that has very water-stressed area. Even some partners are from Egypt. So we are supposed to use the textile wastewater. Some company from Tunisia, some company from, I think Egypt, they are giving us the samples. So we use membranes. So what we do, we develop the membranes, we treat the wastewater from textile industry wastewater, and now we are reaching target at TRL technology readiness level like 9. So that will be commercialized after end of this project, so which is another 1 year from now. And that is what we are working. So how it works? So we develop the membranes by ourselves, different polymers that we use in our laboratory. We cast the membrane by phase inversion process. With the phase inversion process, after that we incorporated nanoparticle on the top of that one that can goes inside the membrane pores. And then under the UV light, UV irradiation, that will be activated. So it is a kind of redox reactions. We perform this reaction in the laboratory scale. Also the semi-pilot scale pilot plant has been built to test this one, so we can create photocatalytic membrane reactors. By the incorporation of photocatalyst, we can treat the wastewater from textile industry or even from pharmaceutical industry to make it more clean so that we can use it in the Mediterranean countries for the irrigations. So that is our things that we are using. And this is what we use. We use titanium as a nanoparticle, synthesized graphene oxide, we incorporated inside the membrane pores. But there are some problems. Problems mean that we need to optimize the process parameters. So to optimize the process parameters, to use the membrane work in a desirable conditions, we need to optimize different process parameters. Suppose it can be pH, it can be temperature, it can be flow rate, it can be feed flow rate, it can be different other things. So we are now trying to optimize these process parameters by simulation. So first we do the experiment in laboratory scale, it's very small scale in a small scale plant. Then data we can go in the bigger scale. We do the simulations to optimize the different parameters. Then we go for the building the semi-pilot scale. And we successfully did it. And this is some of our casting machines, that membrane casting machine that we have in automated, it is automated. So it can heat it up, it can go with a different flow rate, different casting velocity that we need. And we usually use the phase inversion process as described in the first, in this figure, mixed matrix membrane, because that will give the membrane more efficient, more thermal resistance, even the mechanically it is more robust. So that membrane, after that, we use it. So as you see here at the end, that is our membranes. So we can cast not only the flat sheet membranes, but even the hollow fibers, so like tubular membranes. It can have different size. So to make it more, I mean, it can be even the length. The length can be vary. So we can do all these things in our laboratory. So we have the facility to do all these things in our laboratory scale. So this is one of the articles that we publish. So we use photocatalytic membrane reactors to treat the seawater, and we call it plasmonic nanoparticle. This plasmonic nanoparticle was activated inside the membrane surface, membrane pores, and we published this article in one of the very high impact journals. So that is more than 30, I think, now impact factor. So it has been highly cited, and this is the technology that we use. We are using, first of all, we use synthetic wastewater that we created in a laboratory scale. Then we use in the real scale. So real scale wastewater means the company, they send us the wastewater that they generated, and that we use in our system. And we successfully demonstrated that our membranes can separate almost all kinds of reactive dyes from the textile or textile wastewater. Now we are going beyond that. We are trying to use this technology to make it, to use it from the pharmaceutical wastewater, because pharmaceutical wastewater contain a lot of active components that need to be reduced or destroyed before discharging in the sea. So that is what we call it. Pharmaceutical wastewater comes in this one, and we also use the same techniques, same kind of membranes, but with different catalysts. And with this different catalyst, we successfully also reduce almost like 70% of the active components that present in the pharmaceutical wastewater. And we are still working on it. We are developing new membranes almost every day. We are using mostly the nanoparticle that comes from the natural sources, like bio components. And also we are doing like a kind of modified graphene oxide also. It comes from the biosources to use it in this technology. So these are some parameters that we have generated in a laboratory scale. So if somebody has any interest, we can discuss further, because I think we don't have much time to talk about it. And this is the pharmaceutical contamination that we are reducing it. And these are some of the data that we generated. As you can see that we have very good data. So we reduced almost, like as mentioned, 70% of pharmaceutical contamination from the wastewater somehow. And this is the module that we developed in a laboratory scale that was published, one of the first paper in plasmonics materials that published, I think, 2018, and it is highly cited right now until now. And we are using the UV, but now also UV has extra cost. So we are trying to reduce it, to modify the catalyst so that it can work not only in the UV conditions, but also visible light, so that under the visible light conditions, it can also work, perform better. So we are still developing this technology, and I think I'm quite sure that we will do it. And I think these are some modules that we installed, some of the places where the people other people they installed that membranes. So membrane, I think, has a future. So I mean, in all the downstream processing, membrane is the one that need to be used, and it can be everywhere in the world. So people from Europe, Americas, then also Middle East, they all need to use membrane in some point of their life. And I think I don't have. I think this is the last slide. I think they did not put the previous slide, not previous presentation. I think okay. I think this is the last one. I think I don't know why. So after this, I mean, I don't want to go further this, and I think I stop here. And thank you very much for the attention.
Thank you, Professor Chakrabarti, for your enlightening presentation. Now, I'm pleased to introduce Professor Erika Coppola, who is currently a senior research scientist in the Earth System Physics section at the Abdus Salam International Center for Theoretical Physics in Trieste, Italy. Please join me in welcoming Professor Erika Coppola.
Thank you. So good afternoon, everybody. And first of all, I would like to start with thanking the COP16 for the wonderful organization and also the National Meteorological Service for the invitation. So I am a researcher in the ICTP, and my main expertise in this modeling as well as my previous colleague. But my is a special one because I look at the very high resolution scale because I use regional modeling. And then I try to go really at the scale where things are relevant for adaptation mitigation and for industrial development. So in this presentation, I will try to convince you, if you are not, how high resolution in climate matters and what is the difference when you look at projection on low and high resolution, and how is this relevant for water? Because we understood already today that water is the main variable we are interested today here, speaking about drought, desertification, and then to be able to better locate the distribution of the precipitation in any region of the world, and also to predict and project how this distribution is changing, it would be key to develop some strategy for adaptation. So first of all, if we look, for example, at something that is the distribution of the change in the runoff discharge in the world, and we focus on a region, for example, the Saudi Arabia in this example, we see that if we compare the global scale with the high resolution regional scale, there are some similarity, but there are also some differences. In particular, if you look at the small panel on the side, and if you look at global warming level, different global warming level, or different time scenario, if you look at the difference between the global and the high resolution regional model, there are difference of agreement about the model. The high resolution regional model are more in agree that going further in time or higher in temperature, there will be an increase of flood risk for region like the Saudi Arabia. And this is quantified by the variable that is called the 100-year return time of maximum discharge in a region. You see that all the region there is green. And this means that events like, for example, the recent Dubai flood or the cyclone Tay, or as well the heat wave in this area, are going to be more often and happen more often. And the impact of these events, it will be disastrous like the Dubai floods. Why? Because we are not ready for this kind of events, because our land is not ready, and we are not ready to face this kind of events. Then, if we want to try to understand better how these kind of events are attributed, if these kind of events are attributed to climate change, and how these events will become more or less frequent or likely in the future, then we need a proper modeling system and environment to be able to understand that. So first of all, why it does matter to go to high resolution for modeling? As we heard today, and there was just recently today coming out in Science a paper that points to the role of clouds in the, as a main mechanism for climate feedback that is able to enhance the warming of the system. If we refer to the last IPCC report, we see that the major uncertainty in climate projection is coming from cloud. When I go to high resolution and when I use very high resolution model, the process of precipitation and cloud parameterization is not parameterized anymore, because I can be able to represent the convective process without the need of a parameterization. And I can use the original fundamental equation and then integrate this fundamental equation and get the trajectory of my precipitation. Now, high resolution kilometer scale projection are really a reality. under the WCRP umbrella, the World Climate Research Program, and in particular within the CORDEX, the coordinated project, these projections are already happening since at least a decade. We have several regions of the world, like Europe. You see, these are just cartoons that represent how the models are representing different kinds of statistical precipitation. But we have an ensemble of models, regional models, working in Europe, in South America, in Africa around the Lake Victoria, and in the Third Pole in India over the Himalaya. And we are able today to have those models simulating the climate of a region, although we have to use those models on a smaller scale. If you use this kind of model, why are we using this kind of model? Because we want to decrease the uncertainty, right? When we go on a future time scale, we want to have less uncertainty and try to understand better what the process is happening. Are we able to do so? It looks like we have. In a recent paper we published in NPJ, we see that, for example, if we look over the Mediterranean area, at the contribution of the uncertainty of the model uncertainty to the total uncertainty of the precipitation in summer, where we have most of the convective events, you see that the red line is far below the blue line, both in the past and in the future projection. This means that if I use an ensemble, so if I use many models at the kilometer scale without the parameterization of precipitation, then I am able to have a signal that is much more coherent among the model compared to the low resolution model where the precipitation is still parameterized, the convection is still parameterized. But this doesn't stop to the precipitation only. Then if I use those models and want to go even higher at the local scale and look at the projection of the discharge in the river network, do the models still help me towards the decrease of the uncertainty? Yes, they do. This is an example in the Po River, the largest river in Italy. And I use for this simulation, this 100-year of simulation, the data coming from this high-resolution atmospheric model. And if I compare the projection and the change of the discharge between the global, the regional model at the lower resolution and the high-resolution model that are indicated with CP, you see that the size of the bar is decreasing a lot. This means the models are more in agreement, even if I go down the chain of the propagation of the uncertainty. But this is not only the only reason because I want to do so. As you know, the main impacted region of the world are the city. People are living in city. And if I have the resolution to be able to interpret the change of the climate at the urban scale, this will probably help not much the policymaker when they have to plan adaptation and mitigation strategy. So, for example, this is an example by using, again, high resolution of which is the difference between the urban area and the countryside. So, for example, this is an example in Paris, so it's a continental area. If I go and look the daily evolution of precipitation you see in the top and the temperature in the city against the same things in the country area around Paris, I see that the city is able to modulate the peak of precipitation, so the high convective precipitation, exactly after the peak of the temperature during the early hour of the afternoon. Whether this signal is not there if I look at the precipitation evolution during the day in the countryside. This is an important information for the city planner and for everybody that is involved. If I do this for a different kind of city, and I look at how this is in Barcelona, that is studies on the coastal area, I see that there is, again, a different effect. If I look at the daily cycle of the precipitation in the city against the countryside, I see that most of the precipitation during summer is falling during the early hours of the morning in the city area. And the heat highland effect during the day is lasting longer in the city compared to the countryside. this is also something that, of course, is relevant if I want to plan the energy, for example, and the usage within a urban environment. But, of course, what is more disastrous like event are flood. And then if, for example, I use those kind of model, I want also to be able to better detect the floods. These are just examples of flood happening that were happening along the Italian region. And and the question is, how are the model able to reproduce this kind of flood? And what do I understand more if I use those models instead of the parameterized one? Let's take an example of a flood that was happening in 2002 in the northern of Italy. And it was an event that was lasting, it was a quite long event. It was a persistent event. And I want to understand, by using those models, what is happening in this kind of disastrous condition. What is happening in a warming world is that in a similar, if I consider all the conditions that are giving me a similar precipitation distribution of that flood events in the future condition, what I see is that there is a change of circulation attached to these kind of events. So in the upper row, you see the mean sea level pressure and geopotential height represented for the historical and for the end of the century. This is the result of the ensemble of models running without the precipitation parameterization. And in the top row, you see the change of temperature. So what is clear is that the temperature is changing, is increasing. We know that. But what we see is also that there is a shallowing effect of the low level of the low pressure system that is entering the Mediterranean from the western side. If I go and look at the difference, so again, present, future, and change, sorry for the mistake, this is the precipitable water content that I have in the atmosphere. What I see is that in future conditions, due to the increase of temperature, as I expect, the amount of precipitable water in the atmosphere is higher. Therefore, the difference is positive. But if I look at the low-level circulation in the Mediterranean, I see that the wind associated with this depression are slowing down. So I have an increase of precipitable water. So I have more water in the atmosphere that is available for this region, but I have a slower circulation that is making me, the system, staying in the same position as longer compared to the, let's say, colder world. Therefore, this will result in a much more extreme precipitation events. So this is the summary of this particular event. So what I see is that the model, if I run the model in this configuration, I can really go and look at what is the evolution of those events and what is the large-scale atmospheric pattern that are driving these events and what is happening. And this I can only do if I have a model that is able to represent this phenomenon explicitly. So, but then what? How far we are in the regional community worldwide in doing this kind of experiment. Now, if I consider the European domain, usually we are able in the modeling community to simulate hundreds of years of climate for domains that are typically of the size of the black square, with a resolution that is around 12 kilometers. But if we want to go at the resolution of the kilometer scale in domain-wide region, like the red box, the big red box, that is this gray shaded one that I have in this region here, of course, I need much more computational power, and these simulations are going to give me, as an output, a very big amount of data to store. So this is an example of the model running at those resolution. So in the inner part of the box, you see the model that is explicitly representing the precipitation, and you see that there are convection events happening in the domain. Outside the boundary, the ERA5, the reanalysis, are used to describe the same events. Now let's compare how much do I need if I want to run a resolution of 12 kilometer in the black domain compared to if I want to run the same 1 year simulation in the red domain. You see that the amount of CPU hour per year is increasing a lot, but not only, the storage is multiplying by 9. So there is a kind of limit, there is a bottleneck that at the moment these kind of simulations are facing because they are really, really computational demands. So what is the role of AI? So the international community, as you probably have heard and you are aware of, is trying to understand how the machine learning and the AI system can help in this kind of task. And there are several groups in Europe, but also worldwide, and one is us, that are trying to develop climate emulator for the kilometer scale simulation. So we want to use the AI technique to improve our capability to represent the climate at such resolution. What we do, we use some large-scale input at different pressure level, and we try to reproduce the distribution spatially and temporally over a very high-resolution grid that is 3-kilometer grid. And we match this between the real analysis and the model. So we try to develop an algorithm that is learning from the reality, using the reanalysis and the observed precipitation as the best condition we can, and then we use this model to see how it compares to the dynamical model that is doing the same exercise. So we use this kind of architecture, but this is kind of technical things, but to show you that it's a quite complicated one, so we use a combination of 3 kind of network, 2 convolutional, 1 recurrent, 1 graphical one, and we feed the network with the large-scale distribution of 5 atmospheric parameters in 4D variable. If we do so, and we go and look at the flood that were happening in those regions, and we compare the reality on your right-hand side, that is called Grifo, with the machine learning model, you see that the machine learning model is doing quite well. Moreover, our AI model is only trained in the north of Italy, and then we ask to the AI model to reproduce the precipitation, extreme precipitation distribution in the south and in the center. So we are asking to the model to generalize in time and in space. Once we have this model, then we want to know how the model is doing with the model. So we want to use this model to mimic the AI model, to mimic our dynamical model. So now we are comparing the projection for the mid of the century for the true dynamical model, with the dynamical model 3-kilometer resolution, the one that you have seen in the gray box, and the deep learning model, the machine learning or AI model, whatever you want. You see these are the change of mean precipitation, and on your right-hand side you have the world distribution change. But the most important thing is that does this capture the signal of the climate change? So this is the mid of century. What happened if I go to the end of century? Yes, it does. So the deep learning model is able to capture the effect of the warming. The change in precipitation is deepening. The PDF is changing position. Let's try to see if I can mimic that. So I'm moving from a state of lower intensity of extreme precipitation to higher intensity, both in the model world, the red curves, and in the deep learning worlds. So the deep learning method is able to understand the mechanism of climate change. And with this, I hope I convince you that having high resolution projection is key and vital to planning our resilient worlds. There are some references if you are interested in all the work that has been presented. And if you have questions, I'm available here later on.
Thank you very much, Professor Erika, for your interesting and very informative presentation. Now, we will take a short tea break. Please return in 15 minutes as we continue with the program. Refreshments is available here in the right side, and there is the science booths at the back there is the posters there. See you there.
Ladies and gentlemen, please take your seats. The session is about to commence. Ladies and gentlemen, please take your seats. The session is about to commence. Ladies and gentlemen, please take your seats. The session is about to commence.
Good afternoon, everyone, and welcome back. I am Asil Hakami, honored to represent the National Center for Meteorology and to continue this insightful session. To continue our event, it's my pleasure to introduce Dr. Kamil Shahzad, Senior Research Scientist at the National Center for Meteorology, who will moderate our panel discussion on technological innovation for sustainable land management and drought resilience. This discussion will feather insight from exceptional panel for experts in the field. Please join me to welcome Dr. Kamil Shahzad.
Asil, thank you so much. Good afternoon, and ladies and gentlemen, welcome to this highly anticipated panel discussion titled Technological Innovations for Sustainable Land Management and Drought Resilience. Today we have privileged to have with us an esteemed panel experts who bring a wealth of knowledge, groundbreaking research, and practical insights in the field of environmental science, meteorology, and climate resilience. Their diverse expertise will provide a comprehensive perspective on how we can leverage technology to address these critical challenges. So let me introduce first from, I will start from my right side, Dr. Gohar Mehraj. He is a research scientist from University of Tokyo University, Japan. And next, Professor Enrica Coppola, Senior Research Scientist from ICTP, Italy. And at my left side, Professor Lindsay Stringer from University of York, UK. She is the Director of Environmental Department. Welcome, Professor. And from Saudi Arabia, Professor Turki Asiri from King Saudi University. He's our professor in Environmental Department. And at the last, at my left side, Professor Ahmed Saman. He's the Director of Meteorology Department from King Abdulaziz University, as well as he is the Chairman of Center of Excellence for Climate Research Center. So thank you for all of you for your valuable time over here. So first, I would like to start with the, I think, Professor Lindsay Stringer. Your presentation was very wonderful, okay? So we need to actually understand, because you have done so many projects regarding the desertification, land degradation, and drought. So I have just gone through your project Terra Space. You have just worked on this project around the Mediterranean region. There was some specific reason why not in Central or Northern Europe. Yes, yes. Yes.
So the question was why in this part of Europe? Was that the question?
Oh, sorry.
Can you just repeat?
So I will repeat. I'm asking that you have explained in your presentation regarding the project Terra Safe. So it was the country actually you have covered in this project. They are almost around the Mediterranean regions, okay? But you have not focused on any of the country which is in Central Europe or over Northern Europe or over Eastern Europe. There was some specific reason that you have selected only these regions surrounded by, connected with the Mediterranean Sea.
Yeah, so the reason we focused on the Mediterranean region in Terra Safe is because those areas are known to be the most vulnerable to desertification. They have Mediterranean climate, they have large areas of dry land, and we see large areas of water stress as well. And it's great to include Tunisia as well, because obviously there's problems there in terms of the salinity side of things too. So by selecting those 5 areas, we have a range of different degradation contexts where different forms of desertification are taking place.
Okay, thank you. So regarding the, according to the theme of this side event, so adopting new technologies often require significant capacity building, okay? What strategies can be employed to ensure that the local communities, for example, farmers, and the students can have the necessary skills and knowledge to effectively use these innovations?
So a large part of innovation failure is that farmers and those people that you want to use the innovations, they're not involved in the development of those or the design of those innovations from the very beginning. So the first stage is to co-design the innovations. You know, the scientists have the researchers have the expertise in terms of the technical side, but actually the land users, the farmers, they have a vast amount of expertise as well. And maybe their needs are slightly different to what the scientists think they might need. And so by working together, by co-designing it, you're then meeting the farmers' needs while applying the science in such a way that it allows everybody's needs to be met. And in that way, you're building the farmers' capacities as you go, because you're working with them from the beginning. You're identifying the skills gaps and the training that's needed as you're designing and developing the technology, so that when you come to deploy the technology, everybody's ready for it. So this is what I was saying in my presentation about it's not just having technology readiness, we need to have social readiness as well.
Great. So by following your response in this regard, I will now go to Dr. Mehraj. What technology innovations do you believe hold most promise for transforming land management practices and building resilience against drought over the next decades?
Thank you very much, Dr. Kamil. And thank you, COP16 and NCM for providing me the platform to discuss these issues with you. Yes, the question is very relevant because I am yet to show you my presentation. In my presentation, I will show you that there are a myriad of tools available so that we can understand the issue of desertification in the MENA region, because my focus, I have worked in many regions like Mongolia, Vietnam, India, Bangladesh, and even Australia, my main focus has been, my main core area has been using remote sensing GIS for Earth system modeling. But over the time, I have understood this fact that not one technique can be used and one tool can be used for holistic understanding of a problem. So if we need to see ourselves beyond after 2050 or 2070, we need to use a lot of tools together. I was really much impressed by Professor Lindsay's presentation in the afternoon. So the presentation I will be presenting, it likewise mimics different types of stakeholder perceptions are very much important in understanding the models, even taking the model outputs, how to use them. And from the bottom-up approach, all these whether it is remote sensing, whether it is a GIS, whether it is a scenario analysis, whether it is a business type of scenario analysis, I will be showing in one of my slides that we have used a 2x2 matrix to understand different type of scenarios, to show the policymakers what their policies can bring, how their policies will bring change to the future of their own regions. So how the policies of the governments are going to influence the future, this can be studied right now. So in order to understand anything, or I mean any environmental problem for the sake of argument, and more particularly the question of desertification here, we need to think holistically and use a lot of tools together, whether it is remote sensing, whether it is socio-economic analysis. We need to take the help of, like Professor Sudeep Chakraborty's presentation was very interesting, how we can use membranes. Even everything which was today discussed in all the presentations, we have to take everything together so as to develop a holistic understanding and to see how we can see the MENA or localized, whether it is Saudi Arabia or Bahrain or or the GCC countries. We have to use all the tools which are available at present together so that we can really see the change. I often say, I will just end with this. When I went to Japan, my first impression was how Japan went from a war-torn country when it was in the World War II. It was totally, it was devastated. And now I see Japan is so much technologically well-established, developed. So what the policymakers in 1970 were foreseeing their future, now that is happening in the Japan right now. So what they foresaw in 1970 or 1980 or 1950s, that is what is on the ground right now. Likewise, in this region or in any other region of the world or in the developed country, they need to think and prioritize their important things so as to see the future very good for themselves. Thank you so much.
Brilliant, Dr. Gohar. So what steps should be taken now to accelerate the adaptation of these technologies? Professor Lindsay.
Steps for the adaptation of the technologies.
To accelerate this, to accelerate the adaptation of these technologies. So for example, we should start it from the schools, or we should educate to the universities, or we should approach some research centers.
Exactly. We need to have a multi-level approach. So when we talk about schools, we don't just mean secondary schools. We mean raising awareness from a very young age, right up to events, knowledge sharing activities, and capacity building for different stakeholders at different levels. In some countries, NGOs play a really, really important role in awareness raising and training and capacity building. I was doing some work in Nigeria, and we were working closely with NGOs, and they can sometimes engage with groups that it's more difficult for government or for other groups to make sure that they are involved. So I think, taking that multi-level approach, multi-pronged, is the way forward.
Okay, thank you. So now I would like to approach my Saudi professors. So how can emerging technologies like artificial intelligence and remote sensing, climate models, and big data analytics be leveraged to monitor and predict land degradation and drought more effectively? I will go to Professor Ahmed Samad to respond over this question.
Thank you, Dr. Kamil. Actually, before I answer your questions, I'm really impressed by the presentation that actually were going on right here. The most impressive thing is the joint combining different disciplines to serve one particular purpose, which is solving the issue of degradation according to droughts and climate change in general. As for the tools you have mentioned, I would just add to what Dr. Johar has mentioned earlier, just combining these tools. I just want to refer to it as circular or interactive circulation or circular interaction between all these different tools. If I can start with big data analysis, what kind of data we have right now, meteorological data. We also have soil moisture data, socioeconomic data as the beginning. And then how can we use this data using AI techniques, machine learning to improve our forecast accuracy, prediction in general. And then just incorporate these data into the climate models, improving the future projection of droughts and also soil moisture. So it's like an interactive circular interaction between all these tools to serve that purpose.
So I would like to ask regarding the better decision for the to combat desertification or drought. So do you think that we should have the dense observation network, okay, for the better decisions or for better policies? Okay, right from, for example, Saudi Arabia is so big, okay, land-wise, okay, and we have, as Professor Turki explained over here, we have only 28 monitoring stations. So do you think these monitoring stations are enough, or we should enhance this?
We're lucky that we are living in this era with this advanced technology. I mean, satellite, remote sensing techniques. I believe these technology can help actually overcome this challenge. And then it can actually help us improve the managing policy regarding this issue.
Professor Lindsay, what is your take on this to respond to this? That it will be better that we should have a dense observatory network, or the satellite monitoring is enough during this era?
The more data we have, the better, right? So it makes sense to have a dense network of observatories and to have those observations. But I think it's making most of the data as well. So it's not just about collecting the data, but making sure we're asking the right questions of it, we're analysing it appropriately, but also that it's feeding into other technologies such as early warning systems, so that if there is a drought or a flood that's coming, it's being used to its maximum effect so that people can adapt and take action in time.
Okay, thank you. So I would like to go directly to Dr. Gohar. Could you share any recent examples, for example, where these technologies have been successfully applied? I mean, can you share any example, or you can describe any study in which these technologies have been successfully applied? Technology, for example, artificial intelligence, remote sensing, I'm talking about this.
In Japan, for example, when anybody goes out in the morning, and I think this would be the case with any other developed world also, everybody sees because Japan is rainy. Everybody has a backpack, he has an umbrella with him. So their forecasting is so accurate that if they say within 1 minute or 5 minutes there will be rain, there will be rain. And recently they sent I will share you an example, just an example of, it was an earthquake. So all of a sudden they have a system that throughout country, the SMS that we have an iPhone, and if iPhone has a lock, notification lock, if there is an earthquake and it has a, say, after 10 seconds or 15 seconds or 30 seconds it will come, they will issue a nationwide warning, and all of a sudden every mobile will ring, earthquake, 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 earthquake. And within 15 seconds or 30 seconds, we observed that. And it happened to me once I was there. So we could make, so this is the result of a technology. They are using high density earthquake sensors, which are along there. And similarly, they have a very dense network of automatic weather stations also. But we need to see, when we need to, for example, apply in this part of the world, we need to understand how much dense is very much required. So that type of analysis has to be done. If we do so much of density and we don't require so much of dense, there should be some threshold. So that type of studies has to be carried out first, how much dense is actually required. So that, because for example, as Professor Lindsay correctly said, that if there's an early warning system, and for early warning system, this type of high density or automatic weather stations in Himalayas are very much important. But in a planar area where the variation over the topography is very less, so this type of analysis are there and have been conducted, so how much dense is actually required and will suffice our purpose. So I think they are doing the earthquake type of sensor technology has been used in India. I'm basically from India. Uttarakhand has used it. I recently went to Uttarakhand and I saw this technology there. They are now using and they are trying to that integrate this warning system with the cellular services so that everybody knows after any time that this thing is going to happen. Some years before, we were told that we cannot predict an earthquake. One is prediction and one is the early warning. These are two different things. So prediction and early warning system should not be confused. So this is a near future, very near, 1 minute or 30 seconds or 10 seconds. So near future.
So without prediction, how early warning system will work? Can you explain this? Because I could not catch. If there is no prediction, so how we can make the early warning, for example?
Pardon?
So you mentioned that regarding the early warning and prediction. For earthquake, there is no prediction. But we can make early warning. Okay. My question is, without prediction, if we have no idea regarding the prediction, so then how we can make early warning?
Yeah, this is a prediction. Let us not delve into the technical terminologies of the prediction. There is a prediction, there is projection. Many people in the projection fraternity do not use prediction at all. They say, no, this is projection. So this type of things are there, but yes, prediction is there. There are models which predict, which forecast. And that can be used for early warning. So in simple language terms, but if we delve into the terminologies, then there are huge differences in the projection, forecast, prediction. Many people do not consider prediction as a projection also. I mean scientists.
Thank you so much. So now I will go directly to Professor Arika Kubala. First of all, I would say your presentation was excellent. Okay, and being the climate modeling expert, I have really enjoyed your presentation. And there was very interesting things for us because we are also working to adopt this AI technology-based prediction. So would you please explain to us that which are the up-to-date AI applications in climate modeling and climate change community?
Yes, sure. So the main development that you can see nowadays within the climate community, the global and the regional, is either using AI to improve the parameterization of our model. Some of the community are trying to replace the parameterization of the model with the AI-based technology. And this because, of course, AI gains a lot by observation. So wherever you have a lot of good observation, you can be able to develop a model that is much more efficient compared to the traditional one. Because as you know well, the parameterization sometimes are very simplified, like for example, the cloud fraction parameterization. And this is one of the fields where AI can really improve those parameterization by the direct observation of satellite measurement, the profiling of the atmosphere. The other niche where the AI is gaining some field is this emulation. Because as you have learned from the presentation, the demands of the high resolution information is growing. And every other day when you present something, they will ask you, when will you go to this resolution? And then there is actually, at the moment, there is really a bottleneck because there is really no computer in the world that can support a kilometer scale simulation hundreds of years on the global scale. So we have to find a solution for that. And then the solution could be using this AI-based technology to learn from the modeling. So the modeling, the dynamical model are still the center, the core of the research, but the AI can supplement this model and then reproduce some of the variable of this model.
From your presentation, what I have understood that AI maybe after having AI based climate simulations, maybe we required less resources.
To have trained a model that maybe requires the big part of the computational power, because usually the AI works on the GPU technology, so the graphical processor unit technology. These are much, much faster, and they are perfect to handle the exchange of information between the node of the architecture of the AI. So once you have the model trained, for example, to reproduce like 100 of years of precipitation time series at the hourly scale, you need just a couple of hours, compared to the dynamical model that only can produce 1 year of simulation in 4 days of computational. So you can do the comparison.
Okay. So regarding the role of AI to complement the numerical modeling, classical method used so far. So how you will see this?
Okay, so the classical method used so far, if we think about the modeling, the numerical model, I mean, we use fundamental equation there, right? So, I mean, this kind of research, it will never be completely substituted by the AI. But the good news is that the AI research field in this latest year has expanded a lot. So you don't have now only AI that are, as in the past, that are seen as a black box, and you cannot really interpret what is happening within this algorithm. But now, for example, there is this new field of explainable AI, where, for example, the AI-based technology can help you to really improve your classical equation. You can integrate better the equation, like the diffusion equation can find much better solution if it's based on the AI. So it will never be substituting completely the fundamental physics of law of physics, but it will help to speed up the process of the solution, for example.
Okay. So regarding this adaptation of this new technology, it is also the innovation, the AI. So here we have mostly people from the Research and Development Division, Climate Modeling Department from National Center for Meteorology. So what you will recommend to those young researchers and to adopt this technology, and what should do right now they should do?
Okay, so first of all, there are different work already available, and in the most recently in the last supercomputer workshop that has been happening in Atlanta just last week, the Arabian community just got a prize for an emulator that is trying to downscale high-resolution temperature information all over the globe. So I think there are different directions you can go. First of all, we need to study better the application of the AI. Nowadays, the AI has a completely entire research area that is grounded on mathematical understanding, informatics, and physics. And then you have to combine the knowledge and the training on AI and climate in your case. Because being a scientist that is very well prepared on AI algorithm but doesn't know anything about climate, it will be a bit a limitation for that. Instead, if you are able to grow both profile in the same institute or in the same course, this will be much more helpful. So one thing will be improving the training in this kind of field. Second, to explore different kind of applications. Do not just stay with like a downscaler application or a parameterization, a cloud parameterization, but try to explore all the possible applications. And also try to use explainable AI. Now there is also explainable AI that will help you to understand the process that you are studying. And so these are to be all parallel, this development.
Thank you, great. Thank you so much for this detailed response and discussion. So lastly, I would like to go to Professor Turkiya Siri. Sir, I have observed your projects regarding the water management. Okay, so water scarcity is a major concern in drought-prone areas. So can you discuss how technological innovations like smart irrigation systems and water-efficient farming techniques are being implemented to address this issue?
First of all, thank you so much for giving me this great opportunity to join you in this global event, COP16. first, before I answering your question, I would like to mention some declaration from UNESCO's director. I would like to make a brief introduction about this issue. Water scarcity is not just environmental issues; it's a global crisis impact millions of people daily, and world must address this crisis. Audrey Oslo, who is UNESCO's Director General, gave a clear message this year. She said, if we want to preserve peace, we must act swiftly, not only to safeguard water resources, but also to enhance regional and global cooperation in this area. Also, WHO, World Health Organization, there are some key facts regarding this issue. That there are more than 7 million people lack access to clean water. So it's 1 out of 10 people on this planet. The most water-stressed region are Sub-Saharan African and also Middle East, including Gulf countries. Sub-Saharan African has the largest number of water-stressed countries of any region. In 2022, globally, at least 1.7 billion people used a drinking water source contaminated with feces. So by 2050, global water demand is projected to increase by 20% to 25%. Also, there are some factors contributed water scarcities, such as climate change, pollution, also growing population, and efficient water management as well. Regarding your question, we have many technologies overall the world, especially for the developed countries, such as the smart irrigation system, like drip irrigation and automated irrigation. Those systems can help out to reduce the demand of water. Also, remote monitoring for those devices allow farmers to monitor soil moisture and weather condition in real time. Also, there is a water efficient farming techniques like drought-resistant crops and soil moisture management. In most of the developed countries like Australia, United States, India, Spain, have many adapted various modern irrigation method, including subsurface irrigation and sprinkler system. In the Netherlands, the Dutch have developed advanced greenhouse and hydroponic system that use very little water while maximizing agriculture output. We have some examples also locally, if you give me time, or just if you have another question. Okay, at King Saud University, we have good example. We have a good project on the dams. Overall Saudi Arabia, we have more than 550 dams. Most of those dams are ineffective use or useless. Unfortunately, due to the soft soil and with some sediments, those dams cannot let the water get in subsurface. So we implemented a good project to do something regarding this issue, to make an installation for some pipes with some holes from top and bottom for those pipes, just to let the water get in subsurface. Most of those projects, we have more than 22 dams overall Saudi Arabia as a pilot, and we got good results in downstream 40 kilometers at least, with increasing of the level of water in well, and also to get decreasing of the TDS, total dissolved solids. We got for example, in the dam, in Al Ghad Dam, we have the TDS decrease from 2,800 part per million to 1,500 part per million.
Yes, no, thank you so much, Professor. I think you are right. Actually, the dams and water reservoirs will increase the water recharge level in the ground. Now, due to the time limitations, we should end up our session here. Thank you so much for your time and for this wonderful discussion. Thank you.
Thank you to all our speakers and participants for their valuable contribution. Now it's my pleasure to introduce our first speaker for the next session, Professor Biswajit Vardhan, Director of the Center Advanced Modeling and Geospatial Information System at the University of Technology, Sydney. Please join me in welcoming Professor Vardhan.
All right. Good afternoon, good evening, good afternoon. Thank you very much for still making it here. It's a very hard time, right? I have just arrived this morning, all the way from Sydney. And first of all, I would like to thank the organizer, the NCM, and also the UNCCD for inviting me to this forum and to give a talk on this. So, in particularly, I liked actually the concluding part made by you, that obviously machine learning is something taking the whole technology moving forward. And in that space, obviously, we are not just talking about machine learning, we are talking about XAI. So you have made my life a little bit easier because you have already given that platform so that I could speak about my talk, which is how we could leverage the advanced machine learning models and the explainable AI techniques for predicting drought monitoring or any kind of geohazards modeling. Right? We know when you compare between these traditional based methods and also the modern challenges, the modern methods that we are talking about, so there are complexity obviously in the data set that we deal with because ecosystem dynamics and also the interaction between the different Earth system dynamics, actually they play a very crucial role. And therefore, it is very hard actually to identify the patterns and which particularly kind of factor is playing a crucial role in forming or predicting actually an event. So therefore, it is very important actually to apply the kind of model that could be able to particularly understand the relationship between the variables and finding a pattern so that we could establish a mathematical model that which can essentially be used for predictive purposes. And another problem that lies actually in this space is the uncertainty because there are sparse amount of data, not so much of data available, although we talk about so much of data available, and also the difficulty in terms of predicting the events, for example, bringing into the climate model, bringing into, for example, the drought modeling, different types of drought modeling, and so on. So I think I can skip a few slides because you don't need them. We have already spoken a lot of things about this. Let me just straight away go to Australia. So this is where actually I come from. And if you could see, in Australia in the last 100 years, many major droughts has occurred. One is the Federation drought, which started from 1895 and lasted up to 1903. Then the World War II drought, which lasted from 1939 to 45. And then the Millennium drought, which just happened about 10 years ago. So it is from 2001 to 2010. But not only actually we are talking about the traditional drought, but also from time to time we have these flash droughts. That means within the drought, there is a drought that it comes and goes. And it's very hard actually to model them. And this is where actually in the last 3 to 4 years, a lot of research has been going on in this domain. So this is a case study where actually you can see the Walcha area in northern New South Wales. And the entire area was totally dried out. And obviously that lasted, couple of years, creating actually a lot of problems for the farmers and in terms of economic losses and so on. So when you talk about the drought studies, obviously there are a lot of applications, a lot of areas that one could actually work on. So starting from like calculating and developing the drought indicators, like one of the speaker was talking about that in the morning session. Obviously, we have so many indicators, 20, 30 different types of indicators that has been used in this space. And then, but now the question is which one is the best? Which indicators that we call, which indices that we can perhaps be able to, I think Dr. Munir was the one actually who was presenting that. So as you can see from this slide, not only that, focusing on the different types of indices, but we are also talking about how efficiently that we could perhaps predict or forecast a drought well in advance. That is the thing, whether in a 1 month lead period time, 2 months or 3 months lead period time. So obviously the effort should be given more into how well in advance we could be able to predict a drought. So in this domain, this is where actually my today's talk is all about. 2 areas that I would be focusing on. One would be on the calculating and evaluation of model tuning and effects over a forecasted time window. So I'll be giving some examples from the Australian region. And the second part would be identifying the pattern between the different types of drought variables and how well they can be correlated, and can they be able to also contribute towards the forecasting as well. So these are the 2 domains that I will be talking about. Interestingly, when you look at actually, do a little bit of literature review, you could see a lot of work lately. Out of 300 articles that we have reviewed here, we could see a lot of work has been working on in the domain of drought forecasting. So that means a lot of work has been going on this. And obviously more emphasis has been going on climate change, and the most models that has been used lately been machine learning based model, and also support vector machine, and also extreme learning machine based model as well. So this is actually when we did a bit of literature review just on the drought modeling aspect, studying from 2000 to 2020. So looking at this, there are 3 research gaps actually we identified here. One would be how to forecast drought effectively. So the potential solution would be perhaps we could use machine learning. That's what we use here. And then the second research question was how to build trust in the machine learning model, because machine learning models are often known as opaque. They are not trustworthy. So therefore, if we could use the new generation of XAI-based model that can be integrated, that can be able to tell the story a little bit in detail, so that we can understand actually how the processes have been happening. Then the third aspect, the third research question is, how does the extreme dry event affect the vegetation? That means how the vegetation is responding towards the drought. So in this domain, we have used the remote sensing data, Earth observation remote sensing data, to understand actually the pattern and how the response of the vegetation to examine the drought. So therefore, there are 3 objectives that we have identified here. Objective 1, to develop the deep learning-based model for drought modeling. Second one would be the developing XAI-based model for drought modeling. And third one is to examine the vegetation response during the drought. So this is the methodological framework addressing all the 3 research objectives here that I mentioned just now. So I'm talking about here 2 types of drought. One is the conventional drought, and another one is the drought within the drought. That means the flash drought, which is very, very hard actually to detect them. So let me just quickly take you through actually the conventional drought. So in this case, so we used about 8 methodological variables, which I'll be explaining a little bit later on. And then in this case, we use also both types of model, both physical-based model, which is being used by the BOM, Bureau of Meteorology Australia. And then we use the data-driven-based model, which is the machine learning-based model. In this case, the model 1, we use the deep learning-based model. I'm not going into very detail about the modeling itself. And then objective 2, we try actually to bring in the LSTM model, and using the sharply explainable-based model that we could forecast actually the drought. So the data that we use, mostly the rainfall data, which comes from the silo, and the climatic indices time period, as I mentioned, about whole century. That means entire 1901 to 2018. So the second aspect of this methodology is to identify the flash drought, and especially using the evapotranspirations, and then to examine how the vegetation is responding, especially during the flash drought. And the data that we use here was mostly vegetation data products, as I mentioned, Earth observation data products, such as enhanced vegetation index, normalized difference vegetation index, which is based on MODIS. And now also, lately, we are using the new generation of Japanese satellites, Himawari 8 and 9, which gives data at 10-minute interval for the entire globe. So there's a lot of data that is available, which can be also utilized in this domain. Then also use the fluorescence data, that is the SIF data, which is coming from GOSIF and TROPOME. And in this case, because of the time duration that was not available for a long period of time compared to the rainfall data, so therefore we use the 2001 to 2021. So this is the models used for objective 1. Here, the variables, as I mentioned, is about 8 variables that we use, different indices that we use here, that is in different time stamp. So one would be the rainfall, obviously. Then we use the SOI. Then we use the PDO, IOD, because Australian droughts are basically, oscillated or affected by these kind of factors. Then we also use the SAM 903, and then El Nino 3, El Nino 4, and El Nino 3.4. So these are the most important actually variables, climatological variables that affect actually the Australian droughts. So what we did was we split the data because we had 100 years of data. So we split the data from 1900 to 2000 for training the model using the LSTM and all other models that I mentioned. And we used the last 10 years of data for testing the model. So, and this is what actually we predict. We try to predict the SPI 12 for the 12 months prediction. And we would like to see that how well in advance that we could be able to predict the event or not. So these are the different models that we use. Model 1, we use the LSTM, which is a long-term, short-term memory model. And then the model 2 is the combination of the both CNN and by LSTM model. So these are some results of the objective 1 here. This is the left-hand side. What we see is the result of the LSTM model. And these are the five areas that actually we observed. 3 areas are from New South Wales, and the 2 other areas are from the Queensland area, pretty close to the coastal area. So as you can see, the forecasted actually events and also the actual events, they matched pretty well actually. So that means meaning to say, obviously, when you use the machine learning based model, but given that the data has to be good enough actually to establish that relationship. So when you look at actually the results of the CNN by LSTM model, you could see also the similar kind of results are being evident here. And you could see, we don't have a pointer, right? No, okay, so that's what I was looking at. So you could see what we have plotted here. You can see that January 02, December 03, so these are basically the summer times, and then the SPI 12. So most of them actually, they fitted pretty well. The similar case also in the case of attention-based LSTM model. So all the 5 areas, Bathurst, Barbara, Feakle, Colanberry, and Yamba, so we found actually pretty good correlated results here. For the results of objective 2, so in this case we use the Shapley plots. So obviously there are different types of XAI-based models that is being available today, but in this case we use the Shapley plots. So the good thing about these plots are that what it does basically, it ranks the different variables in an order. So in this case, as you could see, in the case of Bathurst, you could see, and rainfall obviously is the most important parameter, and the second most important parameter is the Nino 4. And in the case of Baraba, obviously things have changed. So each and every site, you could see the different types of indices or variables actually are changing. So, and this is the beauty of actually this kind of explainable AI that could tell us the whole story a little bit more in detail, otherwise, which is very difficult to interpret. So the summary plots illustrate actually the variable importance at different locations at different times of 3 months lead. And this on the figure on the right-hand side, it shows the dependence plot. So this shows actually a very shorter meaningful temporal periods to take the full advantage of the information hidden in the temporal trends. Because in this case, obviously, we have 100 years of data, so that temporal scale also can be quite well captured. So in this case, what you could see, essentially the graph is being plotted between the rainfall and the Shapley values that you can see on the y-axis. So they are being well correlated. And while we use actually the dependence plots, Obviously, sometimes it doesn't give you the entire story, especially when you are trying to plot between the two most important variables, because this is what actually gives you the two most important variables. So what we did, in order to try to analyze a little bit more, we went actually one step ahead, and we tried to divide actually the drought into 3 different periods. So one is, as I mentioned, is the millennium drought and the entire drought period, and then the post-drought period as well. So this is what actually you could see here on this plot, that is the trends on the model results at different temporal ranges. So this gives you actually gives you an information about, and you could see on the extreme right column that it shows December and January, February. These are the most critical times, the summertime, where actually the droughts are more evident. And in this case, we use the deep explainer actually to illustrate all these plots and all that. So these are the results, continuing the results of objective 2. So this is the case study of Bathurst, and if you look at actually all those case studies, so what we could see that we have classified the drought condition into 4 types. So basically, we classified into extremely dry, moderately dry, severely dry, and non-drought. But obviously, we know that in the traditional drought, classification, we have 7 types. But here in this case, we have classified into 4 types. And you could see the actual values and predicted values, they are not much of difference. But obviously, sometimes the data also could be an issue as well. So more data obviously need to be analyzed in order to get actually better results. So these are some of the sharp outputs using the CNN by LSTM results. Now, if you look at actually the interpretation of attention-based model results, so these graphs are being plotted between the lead time that is being shown on the x-axis. Then you have on the y-axis is the sequence length. That means in the 12 months period that has been shown. And obviously, the different variables, the 8 variables that I mentioned actually. So in this case, if you look at, for example, the first one, you see that at the 8th month, that means using the SPI 8-month value, it could tell you actually the story of in 1 month, well in advance it can be able to predict. The same thing also goes for, in the case of 2 months lead time, PDO actually gives you a better result in terms of predicting actually the event in 2 months in advance. So similarly, the interpretation plots highlight the importance of large-scale climatic indices for both long-term and long-term dependencies as well. So this is what actually I was explaining in the case of Bathurst. So that means, now there you could see that indices plays an important role at a lag time of 8 months. That means 8th month of SST index was used. So obviously, we use the SST here to analyze this correctly. So now let's look at the last part of the results, which is the flash drought. So flash drought, we know it's very hard actually to predict the flash drought because it's lack of precipitation obviously cuts off moisture supply. Then you have the extreme heat increases the evapotranspirations. Then soil moisture depletes rapidly, low evapotranspiration happens. And then as a result, actually, increase in heating from the surface happens. And it's very hard to actually monitor them, especially from meteorological variables point of view. So in this case, what we did, we used the indices from ESI, which is the standard anomaly of the ET versus ET divided by PET. So these are the monthly time series gaps. What we did, we plotted both daily time series graph for both summer time and also for the winter time. And so these are the flash drought response during the summer. So this is what, based on using the vegetation indices and also, and then when we try to plot the land cover under the flash drought, especially within the 2 weeks, more than 2 weeks, and also the no flash drought time. So depending on actually different type of vegetation that exists actually in the area, they respond very differently during the flash drought. I think we don't have much time now, so yeah, so I would like to wrap it up here. Thank you.
Thank you, Professor, for your insightful presentation. Our next speaker is Dr. Gohar Miraj, Research Scientist at the Department of Ecosystem Studies, the University of Tokyo. Please, let's welcome Dr. Miraj. Dr.
thank you so much. It's going to be a good evening. Thank you so much for providing me this platform to share my ideas, basically. I know I have very little time, 15 minutes, and I will stick to those 15 minutes. But the reason I'm here just to provide some idea how we can holistically understand desertification in the MENA region, Middle East and North Africa. So when I started thinking about it, what would be the innovative tools? I have been part of some studies where we used different types of tools. Then I thought, why to discuss tools, why not to discuss my own case studies and frame it in terms of a framework that would be useful for the MENA region so that they can address desertification holistically. So I will be discussing, I have divided my presentation into 6 stages, basically. One would be the first of any environmental issue is first, whether it is desertification, whether it is air pollution, is identifying the causes, identifying the drivers. Once we identify the drivers, in case of desertification, the next step would be using that to map the vulnerability. And once we map the vulnerability, we also need to understand what are the services ecosystems and natural vegetation and ecosystems are providing. Once we know the models, we try to understand, we do climate analysis, then most important is to integrate the stakeholder insights into our policy making. And once we know the stakeholder insights, we must know the techniques, how to utilize that. For example, in my case, I have used 2 techniques, and I will be discussing those 2 techniques. And finally is implementing the nature-based solutions. In one of the presentations, it was already mentioned that Saudi Arabia has a massive afforestation program to be conducted. So that comes in the nature-based solutions. I will show a study. I was myself part of where we conducted such type of study in Rajasthan, and we particularly showed how much carbon sequestration and carbon credits can be generated using afforestation programs. Let me now move forward. The main causes, the main drivers of the desertification in this part of the world are basically only 4. Maybe 4 also, but broadly 4. One would be the climate change and the variability, the unsustainable land management practices going on. Third one is the water scarcity. This region is already water scarce, but the problem is mismanagement also. And the fourth one is the growth and urbanization. So if once we understand the problems, we then have to use how to assess these problems. In one of the studies we conducted in Vietnam, this is a very particular case study. I will just share you the results. We used innovative statistical techniques, innovative trend analysis to understand the decreasing discharge in the Vietnam region. And the main output which we understood after understanding the 20 years discharge data is that climate change could have been the main driver behind the decreasing discharge. One of the main reasons was the upstream water that was taken away by the upstream countries. So in a region where there is a transboundary ecosystem, transboundary river systems going on, we must not look at a very particular point. We need to understand whole region. For example, in Tigris-Euphrates, in this MENA region, we have such type of problem going on, for example, between Egypt and Sudan. And there is a dam construction by the Ethiopia. And for example, the Jordan River. Jordan River has a similar problem between the countries. And such type of, if we only take one particular aspect into consideration like climate change, we cannot understand the actual picture. That is my concern. So this type of study we can use, there are the tools available such as statistical tools available to understand the decreasing or increasing trends of the river discharges. In another study we conducted in Bangladesh, I am not going to going because already has been much talked about the climate change, and I will really appreciate if somebody wants to know how these case studies were conducted and what were the methodologies. I will be discussing those. But one of the prime indicators of the desertification is the rainfall variability. So there are tools available. We can understand the rainfall variability of the region. Such type of study we already conducted in Bangladesh, where we used different automatic weather station data to understand the rainfall variability of the whole Bangladesh and use it then climate projections to understand what would be the future water stress of the region. In one study we conducted in Mongolia, we used future master plan. We used both the climate change projections and the land use, future land use, to understand what would be the soil moisture condition of the future. So that is also the way we can understand how the urbanization is going to affect the desertification in the long run. In this very particular case, I must emphasize that Riyadh and Jeddah are the most urbanizing areas in the future. So we can also understand this type of tools, such as hydrological modeling tools. We can use them to understand how the urbanization is going to affect the regions of the Saudi Arabia and in any other part of the MENA region. So this is how I try to understand how Mekong study had the key drivers and what are its relevant implications for the MENA region. Once we understand the drivers, the next thing is the most important is the vulnerability mapping. We can use the drivers, we can use the explainable AI tools to map the vulnerable areas which are vulnerable to droughts. Once we understand which areas are vulnerable, we can then actually use the target-oriented intervention strategies. So the next stage, in this type of case study, we already conducted a agricultural drought modeling assessment, agricultural drought, spatial temporal analysis of the agricultural drought in Bangladesh. And in this very particular case study, we used MODIS data and satellite-based MODIS data to using indicators. MODIS has the drought indices. One particular result which is very important in this study was after 2010, we observed that the agricultural droughts were lessening in the region. That coincided with the very good, efficient irrigation policies conducted by the government of Bangladesh. And this is another vulnerability mapping of the Bangladesh, of the northern Bangladesh we conducted, where we used the groundwater well data to understand the groundwater potential mapping and how that will be changing in the future using the climate projections. For MENA, where arid conditions of water scarcity are persistent challenges, using this type of vulnerability assessment will help policymakers to provide urgent intervention and tailor solutions to mitigate the droughts impact effectively. So another study which I showed about the Mongolia region, we can understand how the rapid urbanization and climate variability will be affecting the drought scenario in future. The third stage is the most, I believe, not many people, not many researchers are, or not, I must not say researcher, maybe the PhD scholars and postdoc scholars are doing this, but at the policy and decision-making organization, they are not taking it very seriously. How the current ecosystems are providing us the services. We need to evaluate that also. For example, what is the sediment retention services provided by the vegetation which is currently on the land? We also need to conduct such type of studies, because that will help us in the evaluation of ecosystem services so as to restore that. I am a lead researcher in this study. I conducted this type of study in the whole Indus Basin. Indus Basin is a huge basin. It is divided between the five countries, India, China, Pakistan, and Bangladesh. So this type of study, we observed that where the vegetation is very high, it has high sediment retention services. So this type of understanding will provide us and policymakers an idea that whether particular area should be converted into developmental area or not. So this type of, because they only understand the economic value. They only understand the economic value. If they know that this is economically very important, only then they can understand its importance, whether we should take some area away or not. This is another sediment retention. So if I convert it for the MENA region, for MENA, these insights will highlight the importance of land cover in managing water resources efficiently, particularly in arid regions. So the fourth one, which is the most important, is how to integrate the policy stakeholder insights. How the common people thinks that my policy will impact them, and using their perceptions into the models. So this type of understanding, this will use a socio-economic type of studies. And this cannot be said that this is not important. In this current age, this is the most important, because ultimately this is the common people who will be affected. And it is their perceptions, how they want and what they want. So we conducted this stakeholder perceptions in Bangladesh, and our understanding of how it will impact, we integrated that into the, but main important is, this is my, some of the stakeholder workshops I conducted myself. So advanced tools with the wisdom of local stakeholders will provide the right solution. That is the message. Message is, if you have the advanced tools, if we have the explainable AI tool, if we have the highly efficient memory systems, but unless and until local stakeholders are used in this whole thing, we can only provide on the, okay. So this alignment would provide MENA a resilient adaptation strategy that are supported by local policies. And how to use these stakeholder insights, I myself have been using two important tools. One is the 2x2 matrix, and another is the land change modeler. Land change modeler is the model we use. First I will show you the results of the 2x2 matrix. 2x2 matrix is a very simple type of matrix we use for policy making. We come up with the policymakers and try to show them what are the two critical uncertainties that are going to affect some issue. In this case, in the whole Indus Basin, we developed 4 scenarios. One scenario is the low water, a scenario where there will be low water availability, but there will be high agricultural innovation. So we call that scenario as innovative scarcity. In another scenario, there will be very high water availability and high agricultural innovation. That will impact the, that will be a green revolution in the, say, Indus Basin or the MENA region. The third scenario will be the low water availability and low agricultural innovation crisis. And the fourth scenario would be the traditional abundance. Using these types of, the messages using this type of, overall, there are only 4 possibilities, and showing the policymakers that your actions will provide this type of possibilities. They get better understanding how their policy making in the current scenario will be affecting the future. That is the main message. So then I try to use this type of scenario analysis I conducted for the Indus Basin. I try to superimpose it for the MENA. And the second tool which we use, how to integrate this LCM, with this I will try to complete my presentation, is the land change modeler. I will give an example. I'm part of a, I'm still working on this, and I'm part of a study that has been recently published. We conducted the LCM land change modeler study of throughout Japan. Japan, you must be knowing, is facing one of the difficult situations, that is the population decline. Their population is declining, and because of the population decline, their farmland is abandoning. And Professor, I think, Lindsay also discussed that in Italy. I mean, in some other part, their farmland, they are abandoning because older people are dying and the younger people are not taking over the agriculture as their business. So this type of problem is their big problem. What they do now, they are changing they're tailoring their policies. And how they're changing their policies and what it will have an impact on the future. They are doing it right now. Such type of analysis are being done by the LCM, that is a land change modeler. How the 4, I have just enlisted 4 policies. They are changing the inputs using their policy frameworks and thinking how, for example, if policymakers right now of Saudi Arabia want to see how the NEOM will change the future of Saudi Arabia, how the Vision 2030 will change the landscape of Saudi Arabia, that type of studies can be conducted right now. We can understand what will be the impact in the 2030, 2050, 2070, 2090. Ultimately, I think as researchers, we all are going to die. If we can give something to our future generations through the innovative things, that will be our service to the nation. And as I said, that adaptive realistic planning will be provided by the, once we integrate the physical and social insights, we can provide adaptive realistic planning. Our agricultural innovation in the Indus Basin, if we overlap, we keep it for the MENA region, we can have a resilient underwater scarce conditions. So this is again, the message is that we can continue the local policy making. We can understand what will be the impact of that in the future. Finally is providing the solutions. One important solution is the NBS, that is the nature-based solutions. Our Professor Turki Habibullah today said that Saudi Arabia is going to have mass afforestation. We conducted a study in India, soil anomalies mapping. We showed which areas have deficit soil moisture and which areas have surpluses of soil moisture. Then we did it for Rajasthan, and we used some plant species and tried to see which plant species can be used at a particular region based on the soil moisture. And then we calculated the carbon credits and carbon sequestration potential of that. So this type of understanding is also very important if we have right now, so that our planners can think very, holistically. So nature-based solutions is a sustainable, scalable solution. Vision 2030 will support long-term resistance. And I will, one second. Whatever I said, this comes under the scientific and conceptual framework for land degradation neutrality. This is already a framework of the United Nations UNCCD. So all the 6 framework stages I suggested, they come under avoid, reduce, and reverse frameworks of the SCF for LDN. Thank you so much. And last but not least, this all cannot be done by PhD scholars. Let us be very clear. This has to be institutionalized. An institution like they have already they initiated centers for cloud seeding and all that. This type of holistic understanding can only be developed by centralized institution organization. And I think NCM is doing a great job in that, so they have huge responsibility in taking this forward also. How can MENA look in 2050 if these sustainable, adaptable, and scalable strategies are adopted now? We all have to think about that. Thank you so much. I'm very sorry I rushed it very fast.
Thank you, Doctor, for your insights. And it's a deep honor to have Dr. Ayman Salim Ghulam, the CEO of National Center for Meteorology, here with us. Let's welcome Dr. Ayman Ghulam. Next, we are pleased to welcome Dr. Robin Chakraborty, researcher at the Asian Institute of Technology in Thailand. Please welcome Dr. Chakraborty.
Good afternoon to everyone. Now I am going to present my presentation. The title of my presentation is Climate Change and Agriculture Drought, a Looming Crisis for India's Food Security. We know that the prediction of agriculture drought and monitoring is very much challenging and complex issue in terms of its complexity and irregular nature. So due to this complexity, the drought prediction is very much complex. So there are 2 basic approaches has been associated for drought monitoring system, that is site-based drought monitoring indices and remote sensing based drought monitoring indices. And later on, the application of multivariate descriptive model have been incorporated as an advanced model for drought monitoring and predictions. So when I consider that the site-based drought monitoring system, then different types of approaches have already implemented. These are the SPI, PDSI, CMI, and the evolution of these approaches has mentioned here. When we consider the remote sensing-based approaches, then we found that these approaches are mainly dependent some of the principles. These are the uses soil and vegetation, water intervention to the monitoring agriculture drought, and remote sensing models provide quicker and accurate predictions and accurate data compared to the traditional approaches. In this perspective, different types of the K methods have already been involved. These are the thermal interior model, vegetation condition index, vegetation health index, and NDWI. Then the comprehensive drought monitoring system have been evolved as an advanced model with considering and combining both meteorological and remote sensing data and integrating multiple data sources and improve the accuracy and predicted accuracy also, and robustness of the drought assessment. And in this perspective, different popular indices, that is VEC-DRI and DSI and ultimately MDI. And when we consider the multivariate descriptive model for drought prediction, then we found that the advancement of drought monitoring system has been implemented with considering machine learning and deep learning approaches, and different types of the new and unique approaches have already been involved by different researchers in diversified field for detecting the drought and its predictions. When you consider the deep learning model for drought detection, different types of the advanced approaches has been involved. That is the neural network model and deep learning neural network model, which is considered the sigmoid and softmax function for the classification task. And the binary classification of the drought classification has been done with considering the drought and non-drought, and the performance of the models validated by different types of the popular indices. Here, the Central Highland of India is considered as my study region. This region is dominated by semi-arid climatic conditions, and the states of India like Gujarat, Madhya Pradesh and Rajasthan is associated in this region, and this region is characterized by crystalline, igneous and metamorphic rocks, and diversified vegetation cover is also a common characteristics, but this region is mainly dominated by the tropical dry deciduous forest, and the high drought vulnerability is common in this region due to the irregular rainfall patterns and another causes also there. In this perspective, different types of the drought causal parameters has been considered. This is my study region. The Central Highland of India is considered as my study region. Different types of the causal parameters have been considered. These are the forest fraction, land use land cover, normalized difference vegetation index, soil depth, soil texture, temperature condition index, vegetation condition index, and vegetation fractions. Apart from that, vegetation health index. The agriculture drought has been estimated with considering a deep learning neural network model, and the whole outcome has been reclassified into different qualitative classes with considering popular GIS classification method. And here we found that the very high and high agriculture drought is mainly associated in the western and southern part of the study region, whereas the moderate agriculture drought is mainly associated in the middle and western part of the study region, and maximum part of the study region is associated with very low and low agriculture drought. This is the aerial coverage of the agriculture drought, and the model has been validated with considering different types of the indices, that is the sensitivity, specificity, PPV, NPV, and AUC. Here we found that the AUC value of the DLNN model with considering the training and validation data set are 0.84 and 0.79 respectively, which indicates the optimal capacity of the predicted model, and there is a low chance of the overestimation and underestimation considering the AUC values. Extremely sorry, I think this is not my updated presentation. I have already submitted the updated presentation, but this is not. Okay. When we consider the Indian perspective, the drought monitoring system have already implemented several types of the measures, and found that the already IMD, India Meteorological Department, have already considered the drought prediction and early warning system, but it is not a so complex or complete manner, so we have to work on more, and this type of the approaches can be implemented in the Saudi scenario. Mainly Saudi is facing several types of the conditions like the extreme climatic conditions as well as the low vegetation cover. And another thing is that the low availability of the water resources is one of the major tasks. So we have to keeping in mind that with considering the Saudi's Vision 2030 and green initiatives is one of the major tasks that we have to be conducted. And another thing is that this region is mainly considered as a edit type region, and similar kinds of approaches can be considered in terms of the application of the high resolution remote sensing imageries and short-term dot prediction. Another thing is that Professor Pradhan has already mentioned that the prediction of the flash dot is very much complex due to its irregular nature and shortcoming nature. So we have to keeping in mind that this region also can be facing this type of flash drought due to the climatic uncertainty and extreme climatic conditions. So the proper initiatives in terms of the vegetative cover as well as another method can be implemented. As Dr. Gohar Miraj has already mentioned, that a nature-based solution is one of the main aspect in every researcher, even in the core field or technical field, they ultimately focuses on the nature-based solution apart from that any technical measures or any other strong measures. So we have to keeping in mind that we have to incorporate the mixed approaches like the nature-based solution as well as the technical measures have to be implemented. That's all. Thank you.
Thank you, Dr. Chakraborty, for your presentation. Our next speaker is Professor Claudia Chiriobini, Associate Professor in Water Engineering at the University of Trieste, Italy. Let's welcome Professor Claudia.
Very good pronunciation of my surname. How can I go? First of all, thank you very much. I would like to thank the organizers for inviting me. So, my talk is about water management as a key to build resilience to droughts and climate changes. So we know that climate changes are affecting the environment, especially the water resource, in the ways that some parts of the world are being flooded, whereas at the same time some others are experiencing drought. Moreover, the same region of the world can experience, as we can remember in northern Italy about a couple of years ago, if you might not remember, but we do, especially the Po Valley where I used to live until last year, we had a very dry winter and, well, autumn and winter and spring, and then it came this is the Po River, the largest river in northern Italy, well, the largest river in the whole country, and I used to cycle around along the river banks, and you could even walk across the river. And then a few months later, we had this, so disaster with many damages, and even worse, this is Spain last summer, and this is just a couple of months later in Valencia. So what is happening? Glaciers are melting, and then we have all this river water overflowing and draining to the sea, so more water is becoming salty, and so we have less water available. So famous physicists used to say that we can't expect things to change if we keep on doing the same things. So, but the crisis, it's not always negative. It could be seen as a positive thing in that it pushes us to make discoveries, to invent, to create new strategies. And then I was watching one of my favorite series, Gillian Anderson playing Margaret Thatcher, saying that how will it possibly end up well if we do nothing? So we have to do something. What should we do? We cannot, as far as water is concerned, we cannot continue to rely on the old water management model, in that we store and recharge during the recharge season, so which is in the Mediterranean climates, the winter season, and then we use it during the dry season, which is generally, I mean, in my country and in all the whole Mediterranean basin, the summer season. Because we can have some winters when we had no water at all, and so we have no water, and all of a sudden all this water comes and we are not prepared for it, or we cannot use it. So what should we do? There's something we need to do. Well, I am a water engineer. I graduated over 20 years ago, and back at the time, what they taught us is the classical water storing systems were surface water, but now we start seeing more and more underground water storing systems. What changes if I store in the underground instead of storing in the surface. Well, we don't waste any water. The water is not exposed to sun and wind, so we don't waste any water for evaporation. There's many examples. For example, in Tokyo, they built this, they call it the GCANS project, which is not built for the primary purpose of storing water, but of preventing the city from being flooded. The city of Tokyo is about a few meters, well, 30, 40 meters above the sea level, but there's many channels and rivers beneath it, so it's very vulnerable to floods. But we can also store can also have porosity storage reservoirs in the underground or wetlands, which can also contribute to the purification of water, the cleanup of water. And so what can we practically do? About 10 years ago, maybe 11 years ago, they have started, in China, they started realizing that they had overbuilt and paved everywhere, so urbanization, and started thinking that they had to make the cities more absorbent by implementing the sponge city concept, which then became the Sponge City program. What is its philosophy? The philosophy is that trying to replicate the natural drainage of the land that existed before its construction. So what you see, the graph on the left is a storm hydrograph, which means just the flow rate after a storm rainy event. And the red one is the one before urbanization, the black one is the one after urbanization. So, of course, the runoff is much higher if we pave everywhere, so everything everywhere becomes all waterproof. In Italy, we're pretty good with the laws. I mean, of course, with the laws. And putting into practice, we are also doing, we're also improving, sorry, I got a problem with, okay. So we have this hydraulic and hydrologic invariance concepts, which means that we need to make the flow rate and the volumes approach more the storm hydrograph before urbanization. So working on that, making our cities more absorbent. So how can we work this on? We can start from the small scale, microsystem, the building scale, then go to the medium system, neighborhood scale, and up to the microsystem at the urban scale. And then we need to close the water budget, because we work with closing the water budget in the domain, which is the territorial scale, so the hydrological basin meta system. And so at the building scale, we can put many measures into practice by realizing like detention facilities, green roofs, rooftop gardens, green facades, living walls. They can retain a certain amount of water from each rainstorm and then slowly giving it back to the atmosphere, so preventing. But then we can also have better systems to collect water, like rain gardens, or underground storage and infiltration systems, water squares that can be only flooded only the 10% of the time, and then they're dry most of the time. But also at the neighborhood scale, detention and retention ponds. Then we can realize at a higher scale urban ecological corridors, urban wetland parks, greenways, green corridors. Yeah, it's fine. Auckland, for example, you see here, there was a classification done by a multinational architecture firm, Arup, that was classifying different global cities for their sponginess, and Auckland ranked first for spongy power in that it has many greenways running along the Creek Te Awanga. Sorry, my Maori pronunciation is definitely not good. And connecting different parks. So then we can, at a higher scale, we can have flood lamination areas, green belts, green wedges for northern metropolis. And a very interesting one, which you can't find much material about it, much literature about it, is realizing lagoon areas and the groundwater recharge along the coast. So in my country, so everyone knows that Italy is a boat-shaped peninsula jutting out of southern Europe into the Ionian Sea, the Mediterranean, well, generally the Mediterranean Sea. So there's coast everywhere. And everywhere, every summer, it doesn't rain, and they say, okay, the saltwater wedge is advancing, So if we realize lagoon areas, so I don't have a pointer, but you can see that, along the coast, we create a natural barrier to saltwater intrusion, so to the advancing of the saltwater wedge. And we allow water to infiltrate, to recharge our aquifers. Just to say that we need to take a step back and rebuild. But not only, the United Nations World Water Development Report said that unconventional times need to use unconventional water resources. So what means? It means that, for example, what about harvesting water from fog or turning wastewater into electricity? But this is not such a new thing, because our ancestors used to do that. So archaeologists have found in many places in the world, Middle East, Americas, Southern America, Atacama Desert, and Egypt, some systems to arrange to collect water, so just moisture, water from air. And I'm very proud to show this. This is about a European project I was supervising. I was coordinating in Ferrara when I was before going to the University of Trieste. It was about a project about making cities more livable and about specifically air pollution. So we use this among all measures, we use these anti-smog trees to clean air. So, in order to optimize the water for irrigation for those species, we made use of these trays that were allow the water to be the moisture from air to be collected and conveyed directly to the roots of the plants, so to spare water from irrigation water. So we can also have atmospheric water generators, so harvesting water from air. And I also heard somebody talking about hydroponic crops. Hydroponic crops is a very effective system, so just growing plants by using water-enriched, nutrient-enriched solution. And if we combine it with aquaponics culture, so raising fishes and hydroponic crops, it's a perfect system. It's a closed loop system that recycles and reuses water, and so optimizes water, and we can spare about 90% of the water instead of being wasted by runoff and evaporation. I've also recently heard that the government is making farmers pay less taxes if they make use of these techniques. So the last things I want to show you is about groundwater modeling that can help guarantee sustainable and efficient management plans to build resilience. So this, I'm just showing you a couple of slides. This is about a very complex and vulnerable aquifer system in southern Italy, where we had two aquifers and the presence of geologic faults that are actually acting as a conduit to saltwater intrusion. So what happened is that if we pump and the well are close to these falls, we pump salt water, so we pollute the system, the aquifer system. By elaborating this water quality index and coupling well density and flow rate, we were able to see how can we combine well density and flow rate so that our aquifer system is not vulnerable, is not in the vulnerable zone. Another simulation is about, this is in Emilia-Romagna region, so where it's another very vulnerable system with land subsidence, negative topography, the presence of coastal dunes, and also in the northeastern part, the groundwater height is below the sea level, so we have salt water ingressing. This is other scenarios of well pumping to see how different scenarios of number of wells and pumping rates can to see the different level of vulnerability of as far as the advancing of the wedge, saltwater wedge. And this is other scenario of okay, yeah, so sea level rise about saltwater intrusion. So we see different vulnerabilities, and this is just optimization of pumping in relation to optimization scenarios to reduce saltwater intrusion. Last one is, and then I finish, how to manage what is called MAR, Managed Aquifer Recharge. So the use of recycled and desalinated water to recharge the aquifer. And so the red line is the salinity level that decreases, and the blue line is the groundwater head that increases. So I've finished just saying that we need to respond to nature with nature, and so respond to climate change with solutions that are nature-based. Thank you. How long?
Thank you, Professor Claudia. We will now hear from Dr. Mohammed Adnan Abed, Research Assistant at the University of Oxford, UK. Please, let's welcome Dr. Abed.
Which one? Thank you. So one of the global scenarios people talk about that we can restrict our climate change to 1.5 degree. But recently we have seen from, I'd say, mid of July 2023 to 2024, last 1 year, we have crossed that 1.5 degree sea limit. So that gives us a kind of, clear solution that, okay, if we are in a 1.5 degree C or more warmer world, we could expect more extremes. So already, so this is kind of things which was simulated by the Met Office, and you can see that at the end of the 2024-25 that the forecast was approximately more than 1.6 degrees C. So that was the case. So if I see, and then there's from ESA in Europe, they came out with this statement that, oh, we are experiencing a lot of extreme events because of this, heat waves and all those things. And we have seen that there's a lot of extreme happen in Europe and even in UAE. And recently we have seen flooding. So there are a kind of, gives us kind of a feeling that if we're in a warmer world, we can have some kind of, we could expect some adverse extreme event, where models may not be kind of, give us a good solution about that. So how we can look into the models and how we can find out that is there a way of tackling those things or not? So what strategy we need to adopt in this case? So we have seen from the morning that one of the hotspots in the climate change is the Mediterranean region. And one of the Mediterranean regions, see that the Spain is one of the hotspots, and there's a big agriculture industry over there, which has been affected by the long droughts. And Spain has recently seen a long drought from last 3 or 4 years, and then recently they have an extreme flooding event where it seems to be the local people were very angry about the government, although the event was well forecasted. So how even people take as a forecast, that's another thing we need to look at it. So we need to work with the communities. We need to work with the people that what they require from the climate model people, what they need from us. Do we have an ability to do so or not? So we need to develop the methodology, and we need to look at those solutions. So, this is a famous pair from the Ruthie Bear coming from the WMO people. They talked about this co-production information. Co-production climate information means that we have to work with the users like agriculture, water, energy people, and we talk about them, what they require. It's not only a precipitation, or it's mainly not a temperature. They may require some specific variable, which is like a multivariate variable. So we need to develop not from this side of the thing, but we need to look at from this side of the thing. So for example, we produce information in climate models like rainfall, temperature, and rated extremes. And we say, okay, you can use that information for your agriculture and other purpose. But no, I think that's kind of, force from the climate community. We don't want to do that. We want to learn from them what they require from us.
So for in this case, we need to think about strategy like from the other way around. So we have to think about that, how the agriculture in Spain, what they require, agriculture in Italy, what they require, agriculture in Arabian Peninsula, what they require from the climate community or from the National Center for Meteorology. So in this regard, there's a project ongoing, what we call a SPACT, which means that adopting oriented seamless prediction system. So when we say seamless prediction system, it means that where there are different types of forecasts are available from different time scale. We learned from the morning that there are interannual time scale, there are decadal time scale, and there's a multi-annual which is called projection time scales. So there's a consortium is happening in the Europe based on Met Office and University of Oxford ECMWF. So we are working with this co-production strategy with different people from agriculture, from the governance sector, with the finance people, with the health people, like British Red Cross people, that what they need from us. And for example, if there's some heat wave, how much they will be affected, and how much we can provide the skillful forecast for them, and how far we can provide the forecast for them. So that's the thing which we are developing, kind of co-production strategy with them. So I'll just think about this kind of methodology. So we have different time scales, what we have called seasonal time scale, multi-annual time scale, decade, and climate projections. So we talked about CMAP models, which is climate projection, which is long-term climate projection, and uninitialized models. So when we talk about skill and forecast, we need to initialize modeling systems. So in that case, we need to use the forecast models. So in this case, we have this seasonal forecast, which is having a different models, like C3S systems are there, American models, and many models are there. So in the community, we are producing a new simulation, what we call extended seasonal forecast. Extended seasonal forecast means that the seasonal forecast simulations are available from different start dates for the 7 months. But in extended seasonal forecast, we can forecast for 2 years based on some initial conditions. And then we can merge them, all these kind of framework based on all three things all together to develop a seamless system based from month to multi-annual to a decadal prediction system. So that's a new thing which we are trying to develop. Earlier, there was a project where people have merged the decadal prediction for the climate projection to provide some skillful to the climate projection. But we are focusing on this kind of strategies, earlier half of this case. So what I'm doing here in this case, this is a conceptual model. For example, if I want to target, let's say, 2024 flood in UAE, how far we can forecast this case? I will look at 2 years behind, let's say 2022, and then see, okay, I have a different ensemble. Oh, one more thing which I would like to say, you can see different trajectories going on. So these different trajectories mean there are different ensemble members. So we know that the atmosphere is quite non-linear. So we can't rely on one ensemble member. We need a big ensemble members to get all those things. And of course, and we want to minimize the uncertainties, we need those things. And Erica talked about the uncertainties, which is coming from the physics and all other learning things. And then we need to merge them together with the year one forecast, what happened in 2023 and what happened in January. So we all to merge things together. So give you more clear picture. So this is a kind of, things we're not going to detail. So I will just give you a demonstration. For example, this is what I was saying. If I want to forecast 2024, I will start my forecast in 2022. Then I will keep on, I don't know what happened. Okay, anyway, this was a movie, but it didn't work out. So I will just keep on adding a different way. At the end, you will have a different large ensemble member when we close to our targets in which we are trying to forecast. So for example, the first case study I talked about you in Europe, we are talking about the agriculture user. And agriculture user, we have the big grapevines are there, which is called vineyards in the Spain region. So the main season comes in March, April, when they sow these birds. But if there's any kind of climate fluctuations happen, that affects the industry. And for example, any warming happen or any cooling happen, that affects the industry. So we need to see whether the models have an ability to forecast things ahead, and can they take, based on this thing, can they take some preventive measures? They can put some heat on those things, and those things another thing. So they require very particular variable, what we call frost. which is which is difficult for the models to somehow, some models cannot even do that because we require good microphysics. So I'll just based on this, this is a study region which I'm targeting on this case. So we can see there's a lot of variation, and they complain that in the recent years they faced a lot of frost event, and that affected the industry, and that affected their yield, and that affected that made big losses in their industry. So based on this information, we developed this technique, and if we look at the different forecasts, the black one shows that when we take a different start dates, and we were forecasting at the end. On the right side, we are forecasting, and how far on the left, which is this case, and x-axis shows the lead times and by the skill, and secondary shows the ensemble size. As we approach to our scale, we can see that the ensemble size are increasing, and we are providing a very stable system, which is shown in the blue line, that yes, we can provide some skill based on the long lead time. You can argue, okay, in March at lead 0 we have a better skill, but yes, at lead 0 we could get a better skill because of the initialization thing, but we don't need that, because to take a preventive measure to develop an early warning system, you need a predictions to be done at earlier stages. So this is the case. So, and then we check the reliability in terms of statistics. So close to 0 means the less value has been added to a system, and if, away from the 0 means that more value has been added. So we can see that the longer lead, let's say May lead and August lead, we're adding more added value to a system when we develop this kind of techniques for the temporal merging cases. So this means that for the users in Spain, we can provide them a forecast about 1 year ahead, which is a big news for them. But how, and how reliable and how sharp is that? This we are still trying to investigate those things. So for example, if I talk about Arabian Peninsula, in Arabian Peninsula, there's a recent study that showed that there's a multi-decade variability of drought, and there's a long-term drought they identified in the reanalysis. There's a long-term drought, and we know that in Arabian Peninsula, the main system comes in winter, which is from November to April, and that's a main rainy season, and that affects, which is mainly the Mediterranean climate, based on Mediterranean climate. And if you look at the main driver for this, has been identified in different studies, that there's when there's El Nino, there's a big risk of getting more droughts in the El Nino years during the wet season. So based on these things, and we recently identified it's not the only El Nino, we have only IOD, and we have seen them from the morning talk from Motasim and other people that we need all these driver information to develop a reliable forecasting systems. So we need to put all this information together. So it means that the concurrent events based on El Nino and IOD, they put together, they can make a big impact. And I think one of the most recent examples is the UAE event. There where IOD seems to be a leading part compared to the El Ninos. So if I just summarize all these things, for the things which I'm developing right now is we can provide a skillful forecast for the agriculture users. So the temporal merging allows us to get a big ensemble member, reducing the uncertainties. Of course, the uncertainties really adds to the system. We really need to, quantify the uncertainties, as even Erika pointed out in the morning talk. So we need to think about whether this forecast is being done through a long-term, long-term trends, or there's kind of reliability signals are there or not. So there's a big challenge that how we can develop this kind of climate information, working together with the users, like different people in this case. So in case of Saudi Arabia, I think there's a big potential. You can the NCM has an ability. They have a data. They can talk with the users. They can talk with the industry, and they can see what they required. And based on this, they can tailor that information according to their news. And at the end, I just thank NCM for inviting those things, and thank you very much for listening to me. Thank you so much. I hope I'm on time. Thank you.
Thank you, Doctor, for your insights. Finally, we are pleased to welcome Dr. Kamil Shahzad, Senior Research Scientist at the National Center for Meteorology. Let's give a warm welcome to Dr. Kamil.
Thank you so much. So due to the time limitations, I will try to finish within time. Okay. So I have just conducted some of the, prepared some of the slides regarding the climate-driven drought trends, future projections, and desertification risk in the Arabian Peninsula. So overview, I will go directly to the objective of the study. So here you see the regarding the agriculture point of view, there are two types of water resources which normally utilized for the agriculture purpose over Saudi Arabia. One is the irrigated system, and other is the rainfed. So for the rainfed based agriculture products, southwestern region of Saudi Arabia, there is normally you will see the high rainfall amounts during the summer season as well as there are during the winter season. But over central and northern parts, mostly depends on the agriculture products, depends on the irrigated water systems. So next, here these are the percentage of agriculture products actually produced in Saudi Arabia regarding dates, fruits, vegetables, and cereals, and the percentage of utilization of water to grow these vegetables and fruits over Saudi Arabia. So if you can see here, the highest amount of water has been utilized for Saudi Arabia regarding the date trees, and then the lowest value is regarding the for the vegetables. So this is the actually agriculture products normally grown in Saudi Arabia during the year, and there are some estimates regarding the water consumption for each of the product, how much water is required, how much water is consumed for this. So this analysis, actually this study has been published in the Nature journal. So the purpose to highlight this, that why the drought and desertification phenomena is important for the Saudi Arabia in agriculture point of view. So the major challenges right now the region is facing regarding drought, desertification, and challenges. We have the drought events. Actually, they are not symmetric. Sometimes the northern part of Saudi Arabia is under drought conditions, sometimes the centrals, and sometimes in the southern or southwestern region. So there is no concept that the whole region will go under drought conditions simultaneously. And other is the phenomena is the desertification, I mean the dissipation of the forest. So, and the last one is the dust storm. Dust storm is also another phenomena. Actually, this is also depends on the drought and desertification. So, if you have more phenomena regarding the drought and desertification, the region will face more dust storm and dense dust storm events if these conditions are likely to prevail during in the region. So, next, this is now. I would like to go to my analysis, how I have tried to conclude our study for the drought and desertification. So first of all, I have tried to investigate the historical drought trends by using the observational data set. What is actually the situation is going on regarding the drought? And then what kind of climate drivers actually have the impact over drought and desertification? And then the risk associated with the desertifications and the future projections. And the last one, how we can make the policy and recommendations based on these findings. So here, this is the analysis. You can see I have just restricted the annual rainfall climatology maps for the period from 1981 up to 2023, just for the assessment that how the rainfall patterns actually appears over the region. So here you can see that the Saudi Arabia receives maximum rainfall over central, northeastern, and southwestern region. And it was really surprising for me if you look at the annual rainfall trend. So rainfall has the increasing trend over northern, western, southwestern, as well as over the eastern regions at annual time scale. And this is the area average of rainfall intervariability for the whole Saudi Arabia. And you can see after 2015, the scenario has been changed for Saudi Arabia. Saudi Arabia is receiving from last, especially from last 5 to 6 years, historical records of the rainfall appeared over the Saudi Arabia. And there are very less drought events during the last 5 or 6 years. And regarding the SPI, the meteorological drought index, I have constructed this by using the Shrif's rainfall data set for the same period. And if you look at this, only the meteorological drought, Only the meteorological drought is more has a more trend over the southern and central region and comparatively to the eastern region. Other regions, for example, the western regions and the northern regions, there are mostly the wetter conditions are prevailing, and it shows that the increasing trend shows that the region is going to more towards the wetter conditions as compared to the drier conditions. This is the regional, actually, the assessment of the meteorological drought events. So I have just constructed this time series over the region for northern region, for central region, southwestern, and the eastern region. So in all these regions, if you look at this, after 2015, in all of the regions, mostly in most of the regions, there is no drought condition. Rainfall has the new records after 2015. But if you look at the over the Rub al Khali, the desert area, and over the northern, over the central parts, climatologically, there are more drought conditions are prevailing, and it makes sense because these are the desert areas as well. No, for this analysis, I think just Dr. Adnan Abid has discussed over this. So I have constructed this SST composite map based on the drought and wet years. So if you see for the top map, it is from November to April SST anomaly composite map during the drought years over Saudi Arabia. You can see the La Nina actually enhances the drought conditions, are likely to trigger the drought conditions over the Saudi Arabia. But for the summer season, extended summer season from May to October, if you see that the weak El Nino or El Nino type pattern actually causes the drought-like conditions over the Saudi Arabia. So this is the opposite phenomena actually has the effect over the rainfall. During winter season, the La Nina will cause the drought conditions, but during the summer season, El Nino conditions are likely to enhance the dry conditions, which will favor to the drought conditions. So for the case study, I have selected just one of the region in southwestern region, Asir and Abha region, to find that how the desertification actually taking shape in this region. So the above map shows the area average time series of a meteorological drought event over this southwestern region, Abha and Asir region. You can see this, it shows the increasing trend, tilting towards the drier conditions, tilting towards the wetter conditions. And same thing is reflecting. I have prepared the NDVI map, normalized difference vegetation index, which is actually the reflection of the radiation measurements. So for 1990 year and year for 2004 and year 2008, and last one in the corner, you can see it is for year 2022. So year 2022 is actually lies in the year in the last years, where you can see the rainfall actually the meteorological drought shows the increasing trend in respect of the precipitation increase. So vegetation index is also positive over this region. It means that it is going to favor to finish this desertification condition over southwestern region under the influence of this climate variation. Here I have used the 24 CMF6 models without going to do their validation and verification analysis, because I just want to, I have used a different approach based on the tercile calculations. So here you can see that the rainfall climatology for the base period, I have taken the years from up to 2014. So the observation map and CMF6 maps, comparatively they have the similar type of patterns. And if you see at the annual cycle of rainfall, observation rainfall, and the rainfall history from the CMF6 models, the cycle is almost, the pattern is almost similar to the observation. So we can say that overall CMF6 performs, comparatively performs good to reproduce the climatological features for the rainfall over Saudi Arabia. So here, I have just created some probabilistic mapping for projected meteorological droughts. So by using the SSPI 2.6 low scenario and with the highest scenario SSP 585. So here I have used this approach based on the tercile. So what I have done here, I have just consider the years which have the value, for example, 0.5 of the standard deviation above than 0.5 standard deviation, it will be considered as the wet year. And if the value of SP index will be less than 0.5 of the standard deviation than the mean, it will be considered as the dry year or drought year. And between this value, it will be considered as the normal year. So if you see the changes based on this probabilistic approach, if you see the SSP during the period from 2026 to 2049, the near future period, you will see mostly mostly CMF6 models are in consensus that there are chances of the wetter conditions over southwestern region and the eastern region. Only the central parts will be under the drought conditions. So all of these scenarios from a near future, mid and end of the century, they are showing, mostly models are in consensus that only the southern and southwestern region may have the chances of more rainfall over the region, and the central and northern parts, maybe central parts will face some drought conditions, but overall it will remain normal over the northern and northeastern regions. This is, I have, by using the CMF6, these 24 models, I have taken the area average for whole Saudi Arabia in top maps, then the northern for the central maps, and the southern by taking the area average of meteorological drought index over the southern half. So from these we can see that there is not significant increasing trend in any of the projections as a consensus. Okay, but one thing is observed. With the increasing of time, for example, mid-century and end-century, it shows that there are chances of more extreme events in respect of rainfall or in drought conditions. So the frequency of extremes is likely to increase at the first glance. So regarding the trends from the probabilistic maps, it is clear that the rainfall is likely to increase over southern and southwestern region, but overall the extremes are likely to increase, especially over northern region. Northern regions is likely to face more extreme events in respect of drought and wetter conditions in the future periods. So lastly, the challenges, for example, the drought and desertification. The drought has the challenges, for example, food industry, it will impact over the food industry, economic losses, and the water scarcity, and the desertification will have the impact over biodiversity, loss of arable land, and migration. The solution is for the drought, what is the solution should be? AI-based water management, satellite monitoring, and precision agriculture, cloud seeding, and for desertification, the possible solutions can be generated from renewable energy for irrigation and soil restoration technologies. Thank you.
Thank you, Dr. Kamil. And now we will display the event outcomes for today's event. So the first outcomes is adoption of technology-driven solutions. Second, enhanced international collaboration. Third, increased awareness and capacity building. The fourth, roadmap for future land restoration efforts. Fifth, advancement in climate data utilization.
Hello everyone. Actually, these outcomes are designed only for our open discussion. Okay, because I think anyone from us can suggest regarding the outcomes. Okay, if someone recommends something to us, he's most welcome. Okay, so these are the outcomes. So there is any output or feedback from our speakers, it will be highly appreciated.
Hello. Yes. Thank you very much. Thank you for all the speakers and participants and the organizer for these successful events. Actually, this is the, as Dr. Kamil mentioned, this is the outcomes expected from the panel discussion and through your abstract for the last few months. So, inshallah, we will send it through emails, and we are very open-minded for more suggestions or to enhance these outcomes. Thank you so much.
Thank you, Dr. Abdul Karim. I would like to extend thank you to all our speakers, panelists, and participants for their valuable contribution and insightful discussion. Your engagement has been instrumental in making this event a success, and we are grateful for your time and efforts. Thank you once again, and we wish you a pleasant stay in Riyadh. Thank you.
Can we come just along here? We need to have just a picture, yeah, photo. All participants.